Hello. Welcome to Automat Live Coding. I am doing some changes in the stream setup. That's why the stream started later today. And I still haven't finished. I have no idea what I'm doing, but it's fun. It's fun. So now the stream has more layers. I still don't know what to do with them. There they are. So we have a tiny view of my desk. So you can see I'm not moving mouse when Automat is doing stuff. And I ditched the green screen. You know, it's sitting right there. So now it should be possible to kind of insert windows between, we should be able to use more full screen windows now. The background foreground separation isn't perfect. I mean, there was a decent filter here that worked really well, but I'll try to switch this over, so maybe I don't know if it will crash the stream, but I will try to show you the better alternative. So background removal can be switched to this. Okay, and I'm not sure if you can see me in real time, but this method seems to work slightly better. Switching this back to whatever I used last time. Anyway, if it was possible to run that method asynchronously, for instance, it would be ideal, so that I could start it and then reuse the alpha channel from multiple frames ago. Unfortunately, no, this is the bane of standard software architecture. I can only change the settings which are exposed in the user interface. I can never peek behind the scenes, which I would love to. Anyway, so this setup is going to allow us to watch some YouTube videos while coding more efficiently. I can now work at regular resolution, and the videos will be displayed somewhere here. And this is another thing I'm setting up. This is the FreeTube client. Today we are going to watch a video about finishing software. So Better Software Conference that we watched for the past couple of streams has more interesting videos. We watched them initially, so we will not be rewatching them in the chronological order. It's a video by Eskil Steenberg. Anyway, he did two presentations on the conference, and one of them we'll watch today. Just a moment. I think I will have to pick a reasonable size here. Just setting up some things. I'm finally using my streaming PC, because streaming PC has a decent GPU. The GPU was only used for encoding video. Now it's actually used for the foreground-background separation as well. Window capture. I can even capture the audio from this window. Nice. Ooh. Let's do some cutting. Maybe here. It's a good place. Right in the center. And let's see if this works.
Of libraries, he is on the
Seems to work. Ooh.
C Standard Committee.
Nice.
And he has some spicy C opinions as well. So hopefully we'll hear it. So give it up. A round of applause for Eskil Steenberg Hall.
Is my mic on? Yeah. Good.
Yeah, it's adjusting the
So,
volume.
hello, everybody.
Should be good now.
I'm just an introduction for people who don't know me. Maybe in the community, I'm mostly known for a video called How I Program C, which is far too long. But over the
Okay, before we go in this stream, I have a fairly boring piece of code to fix. That piece of code is the timeline code. I decided to finally do some of this splitting that I was promising for a long time. Splitting objects and widgets which are rendering them. It was like working around this issue, it just feels like a bad use of the time. So we will be doing this here. For instance, location. I mean, location is still a widget. Location is a special widget. It will probably not be a widget for long. So this is the thing that we're working on right now. Actually, we only have problems with this, with timeline, and with keypresser. Those are the only two objects which are causing issues for us right now. So they are the priority. Anyway. We should be able to do it like that, so that the string is somewhat visible. Okay, let's go.
years, for some reason, it's gotten 800,000 views, which is crazy. I wrote a long time ago, I wrote a real-time...
Maybe you should actually watch this background, how I program C. Let me add a bookmark here.
give a talk that I gave in Seattle a couple of weeks ago, and it's about C programming. So this will be archived, yes, and I'm going to talk about like how I program and my style of programming. And this is kind of an advanced talk. It is about advanced C programming. On the other hand, it's kind of made for people who don't program C. So if you are a programmer that program, another language, you probably sort of superficially know C. You know that it's that language that has pointers and it works like all the other languages except it doesn't have a bunch of stuff, and therefore it's harder and it's evil. Most people have learned C at some point, but since most people aren't actually programming in C, they're using Java or some higher level language. They don't actually know how to make something in C. Like, how do you build a real application? So that is what I'm going to
I'm adjusting some
talk
levels
about.
so that the volume
So I think C is the greatest language.
is
I don't think
balanced.
that C is a perfect language, but I think the reason why it's a language that is 40 plus years old and still haven't been beaten is because people who design languages try to do things that I think are wrong. I think their assumptions about how to program are wrong, and they're trying to solve the wrong problem. And it's not obvious that C does things right, and that's why people don't try to, do something that is better.
The C language, when it was designed in a very different environment. Nowadays, when we think about languages, we really think about ergonomics and different mathematical formalisms that can be applied to synthesize a program. But when C was conceived, it was more like a portable way. I mean, it was based on Algol, the Algol's expressions, like maybe even before Algol, those expressions were present. Anyway, C was mostly seen as a more convenient way to program, and C was criticized as being inefficient because to program in C, you have to follow a calling convention. And in assembly, you don't have calling convention. So C was seen as this slow and inefficient way that lazy programmers use because they don't want to write proper assembly.
Better than C, they're trying to do something different. And that's kind of what I'm going to explain today. I'm going to explain what the things I like in C are and how I think quite differently about programming from other people. You can definitely argue with me, and I think that's good. I don't think that everybody should agree with me. I'm going to say some controversial stuff, and that's totally fine if you don't agree with me. But I'm going to give you some reasons for why I program the way I do. And I think if you check out my website or any of the code you can see that I'm a very, very productive programmer. And therefore, I think that I can at least a little bit back up the fact that the way that I program is not entirely stupid. So the first thing I want to say is yes, in the beginning, you always want results, and in the end, all you want is control. And this is something that is like very true for almost anything you do. Like, so imagine if you're building a web page, which most people have done. So when you start out making a web page, all you say is like, oh, I just want to put this text on the web. I don't care. Why does it have to be like tags and crap like that? Like, can't I just like put the text up? Why do I need like CSS and files and whatever? This is stupid. I just want my text. And as soon as you put your text up, you're like, wow, that's really ugly. I want to change the color. I want to change how it looks. So you do that. And then you realize you can set, a tag called color, and that looks bad. Then you start saying, oh no, I want it to be a different color, and then you want more stuff, and eventually you're going to want to tinker with everything, and in the end you're going to say, why doesn't HTML doesn't that feature that I really need? Why doesn't it do everything I want? So you started out not wanting all those features, and in the end you're complaining that there isn't enough features. And therefore, you should know that from the beginning. And if you know that, oh, there's a bunch of complexity in this, but I'm going to want that complexity. So I'm not going to be afraid of that complexity. I'm not going to complain about the complexity. I'm going to say, this has reasons, and I'm going to embrace that. So the example I have right in front of you is, you go into a kitchen, either you say, I just want an omelet, making me an omelet. Why can't this kitchen make me an omelet? And another way of walking into a kitchen is say, what do I have in this kitchen? What can this kitchen provide me? And if you allow the kitchen to sort of show you what it can do, and you find new interesting ingredients and new interesting tools, then maybe you can make something way more awesome than if you just like, I just want the omelet, and I don't care how it's made. So that to me is like really key, that if you want to be a good programmer, you're gonna have to want to learn how to do things. So that's like my first thing, and that's really colors a lot of why and how I program. So typical example of this
Kodiakula says,
is memory protection.
So,
Garbage collection. So garbage collection is for people to say, well, I don't.
so what Eskil said, I agree with him. So he said that, I mean, like that looking for immediate results will probably lead to more problems. There is this really good approach for learning programming, which is based on just playing with programs, not trying to build a big project, but rather learning a language feature and then playing with it for some time, pushing it to its limits. That works very nicely. This is the approach that worked for me. But it seems like he has something different in mind for the next part of the video.
I don't want to have to care about memory. I want to just like not have to free memory and get memory leaks. Just deal with it, and that's great in the beginning. But once you get far enough along, and if you make something that needs to run fast and things like that, then you start caring about like performance. So
Be right back.
then you have to try to make it not do garbage collection all the time and at the right point, and you don't have a control over that, and you start hating it. And after a while, you wish you had free. You wish you had the ability to say, I want to free this memory now. Do it now because now is a good time to do it. And the lack of control is actually not a.
Okay, I will pause it for a second because before I continue, I want to think through a problem I have right now. It's that when a timeline is being edited, it can be edited in a background thread, and the client thread, which is rendering the timeline, may have some issues. Ah. Oh yeah. Okay. Is it something I can draw maybe? Let's try to draw this. So let's use a scratch. Let's have a timeline for the so Automat is not single-threaded. Updates can happen on any thread. So there could be something is happening in the operating system. And clients. So there is a client. Let's call this render thread. So this is where widgets live. We can add some music. And there can be multiple render threads if there are multiple clients connected to Automat. And let's call this render thread 1, render thread 2. There is let's say a temporary thread started. It could come from operating system. For example, I moved my mouse or something happened. Macro recorder created a new track. So this method is called. It happens on a different thread. So the timeline is changed. Now, when it's changed, we need to somehow notify those other threads that they should reread the timeline state. They should reposition all of the child widgets. Like this can even happen when I'm just scrolling around. I'm scrolling left, right. It's going to update the timeline. So I need to somehow propagate this change. And the render threads, it's so messed up, because on the render thread we also have two separate actions. We have tick, periodic tick, and tick is typically what updates the hierarchy. So this is where we would usually reposition child objects, and there is draw, which draws the whatever is stored in the widget. So this could cause problems. Oh yeah. I think in general, we need a good way to synchronize widget hierarchy. I think tick is actually a very good place to add, update, or remove child widgets. How do I send this notification? So there are just two ways of sending cross-thread notifications. There are critical sections, like, or maybe more. There are also atomics, but atomic is unusable here. And message queues. Those are our only options for communicating between threads. I can, instead of this update child transform, I can do wake widgets animation. And this is called during tick anyway. I could even inline it, this. So during tick, I am using a critical section. So I am actually locking a mutex within the timeline and updating the widget hierarchy to match it. Okay, let's see, this is going to be enough. Because there is one more thing I want to do. I want to make sure that if the update is not a full update, if the update is just a simple transform change, you know, just shift the matrix a little bit so that the texture is going to be rendered at a proper position. I want this to be faster. It doesn't seem easy. Okay, I will figure out a solution for low latency updates maybe a little bit later. Because in the rendering pipeline, after tick and draw, there is the anchor update step as well. So maybe I can somehow tie into that. Anchors could be atomic. Okay, that sounds actually reasonable. Can go back to the video.
Problem. It was sorry. The lack of control is the problem. Whereas, you know, doing the manual work is what you wish for. And I spend about 20 minutes a year looking for memory leaks, and I'll show you some cool tools that I have to do that. And it's a solvable problem because I have the power to control memory. Whereas if you don't have that control, you may at some point hit a wall. It'll be really easy in the beginning when you don't care, but then when you do care, you're kind of screwed. So that to me is like a really good example of that. And the other thing I'm trying to do when I program is I try to keep my technology footprint really small. So, people in programming world, they tend to talk about new features. They talk about like this language does this and I don't have to do that, or I have to use this library and blah, 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 blah. And to me, that is just stupid. I use C89. C99, which is now 17 years old, is still too new. It's also broken. We can talk about that if anybody wants to know why, but C99 has actually been fixed in C11, but C11 is super new and isn't implemented. And when I write
All
code, I
this
want it to run
video.
on anything. I don't know which compiler I'm going to use in the
Oh,
future.
it's almost 10
I
years
want to be
old.
able to have the simplest possible compiler compile my code, and the more stuff I require, the more things I do, the bigger my footprint is, the harder it is to run, and the more fragile my code becomes because there's more things that can break. Whereas if I use very few things, my code can't break. So that's really important. I have 0 unwrapped dependencies, which to me is really, really important because I don't trust anything in the world. Every company, every operating system may disappear, they may go bankrupt, they may not, they may change something at any point.
Yeah,
And
I
if I
like that.
use
I
that
agree.
API in a million different places,
It's okay to have the dependency if you kind of switch it out for a different thing, or I mean, you have to kind of predict how likely is the future of this dependency. Is it going to be turned into a paid program and shitified essentially, or not? If not, then it's probably fine.
I'm basically screwed because someone else took a decision or made a bad decision that I have no control over. Therefore, I want to wrap everything so that I have 100% control over all my code. And that's really important for me. The code that I write is going to live for decades. And some of the code that I use, to this day was written 15 years ago, and it works beautifully today. And that's really important to me. I'm not interested in hacking something together that's, is alive for a couple of days. I want it to last forever. And so having a small footprint is really, really important. So let's move on. So this takes me to another thing that I think is kind of different from how other people think about programming. And when you listen to programming, people, they say, "Oh, you can do this in 2 lines of code in this language. It's amazing," and that to me just sounds incredibly backwards because to me, typing is never what's hard about programming. I would rather, do 10, 15, 100 lines of code that doesn't have a bug in it than have 2 lines of code that does have a bug in it. Looking for that bug is usually going to take a lot longer than typing the actual code.
This is, I think this is a misrepresentation. And it's not like the terse syntax is more buggy. Bugs are just as likely in a terse code and in a longish code. Maybe the redundancy helps a little bit catch the bugs. But I actually think the shorter, if a language actually has facilities that help make express the same problem in a shorter way, then it probably is a little bit less likely to have bugs because the language probably takes care of common issues, common edge cases. Like you can have a hash map, right, in high-level programming language, And that hash map will probably correctly handle missing keys. But if you're implementing hash map from scratch, you run into those edge cases and you have to handle each of them. It's easy to forget them. Bugs are not only caused by mistakes in the code, but also things that are kind of not there. And when you're writing everything from scratch, that's the more likely kind of bug.
And that brings me to a really interesting observation, which is that we think of code as a way to communicate with computers, and that's obviously true. We give commands to a computer to do things. That's what code does. But actually what's equally, if not more important, is that code communicates to us what a computer does. And therefore, you spend more time reading your own code than the compiler does. And that's a very interesting observation, that your code has to be readable to you. And if you read your own code wrong, you don't understand what the computer does. And therefore, it's really, really important to read your own code and understand it. And your code has to be clear to you. And therefore, there can't be any misunderstanding between what the compiler believes you wrote and what you believe you wrote. And therefore, ambiguity is the enemy, right? So you want everything to be incredibly clear. If the compiler doesn't understand what you do, you don't want the compiler to say, I'll just guess, or I'll just figure it out, or I'll just, wing it. You want the compiler to be like, hey, stop. I don't understand this. Explain this to me. Give me an error. And that to me is like really, really important, that you want errors. You want the compiler is your friend when it tells you something is wrong. That's a way of it catching you doing something wrong, or you not being clear about what you want. And that's a good thing. So, a lot of people say that, it's really like discouraging to have the computer tell you error, wrong, bad, but actually it's a really good thing. So more errors, more communication from the compiler, less ambiguity. And C++ to me is a terrible language for this very reason. So C++ tried to be clever, and cleverness is like the root of all evil. It's
I see.
Premature optimization.
I mean, there are different kinds of bugs that happen if you write from scratch, like missing error handling, or like missing some edge cases, which are typically well handled by the standard libraries.
And the worst thing about C++, in my opinion, is that C++ allows you to do some clever stuff that makes you think you're clever when you're really dumb. And people are sort of proud when they use features.
Templates are like that. Obviously, he's talking about templates. For whatever reason, designers of C++ decided to roll out a completely separate language, almost within language, for working with types. It's very bizarre. It's a source of a lot of issues when anyone tries to learn C++. So whenever you use those angled brackets, you're entering the world of templates. Error messages are really bad. There are some modern approaches to rethink templates. Zig is a great example. Zig has compile time, essentially evaluation of the program. There are structural macros that some other languages choose to go for, which are also nice. I think JavaScript has them. I mean, JavaScript has a lot of extra languages which are compiling to JavaScript, but they do this kind of stuff a lot. You write in a slightly different language which compiles to JavaScript. JavaScript is like a backend.
Operator overloading and things like that.
But when you use them with restraint, it's fine to use templates. And even if you abuse them, that's fine. Like, it's good to have some fun programming.
Doing stupid stuff.
It's just good to not have fun when you're programming, critical software, like software that people will depend on.
And another thing about C++ is that it tries to hide things, and I think that's the root of a lot of evil. You don't want to hide things. You want things
Encapsulation.
to be explicit.
It's
So
not only a fault of it's not really a fault of C++. C++ doesn't really try to hide anything. It gives you tools such as private annotations and friend annotations that you can use to hide information. It's a purely formal hiding. If you are determined, you can pierce through the veil of private members, which can actually be a source of surprise for programmers. So this private thing in C++, it cannot be used as a security boundary because it's so easy to bypass. It's just to discourage looking inside. And it's probably something completely unnecessary. It's probably something that could be removed from the language, I agree. It's a result of some very old ideas how programming could work and should work. There is this idea that encapsulation is a key component of object-oriented programming, and encapsulation understood as hiding of information. It makes sense as for robustness, for security, but we have better mechanisms for this, such as process isolation, or like containers, even. Within the application, it's often good enough to mark some properties as, implementation detail, but still allow whoever to access them.
check out some examples. Operator overloading is just horrible, and usually what people say.
It's not that horrible. It's you can use it to write really nice idiomatic, expressions. Like this one, for instance. So typically when you multiply vectors with this asterisk, it's an element by element multiplication. For dot product, people usually use something different, like a dot function. And yeah, operator overloading. So I think a lot of the complaints that the author has are based on strawman arguments. He takes a language feature, he abuses it, and then he says, look, it can be abused. Every language feature can be abused. Sometimes there are good reasons to abuse them. So just having an option to do something is not bad.
Says like, well, it's bad, you can do bad things with it, but it's really good for some things like vector math, right? You can build a vector type that just and then you can write, vectors, and it's awesome. And then I usually show them this line where you have, two vectors and a multiplication between them.
I don't think anyone uses asterisk as a dot product. This is just a made up thing. Anybody who sees this, who actually uses dot products, always has a separate function for this.
And then I ask them, what is this? Is this a dot product or is it a pairwise multiplication?
It's an element wise.
Usually if I'm with a group of people, everybody says, well, that's easy, and then half the room says pairwise multiplication and half the room says dot product. So basically,
I don't think so. I don't think so.
But it's not. And therefore, read the code below. This can't, be misunderstood. This is ultra clear. This is a function that takes the.
But there is another issue about this code. Look how many times does it repeat vector. It's 4 times per line. And in C++, if you wrote this, you would usually have vector as a type. The name of the variable would be just A. Or even auto, because types can be deduced. So auto A equals B times C.
These thing, and it does multiplication.
It's very compact. but it really doesn't invite a lot of errors. When you overload operators, you have to be very clear about how you're using the overloaded. What's the meaning of overloading for you?
And dot, and it's, you know, you can't mix these two up, and that to me is like much better. So this cleverness is just like, it makes people think they're smart when they're really doing something dumb. I think I have some other thing. Yeah, so you have, you know, overloading here, and that again is, you know, one of those practicalities that people think are awesome. So here I have
It is awesome.
implementation of add.
It is awesome. The only issue is that the rules about choosing a specific overload are sometimes unclear, because if you work in, especially in multiple namespace scopes, it's often hard to think which namespace scope function is going to be resolved. So it's a source of some issues. If you do this properly, it's not an issue. If you don't have, you know, you could have all your functions named the same and just put them in different namespaces, then it would be madness.
They're obviously what they do. I have for integer, I have for float, and I have for doubles. But then
it was recorded almost 10 years ago, this video. Nowadays, C++ would, I mean, if you were doing something like that, you would probably do this with a template and maybe add template specializations here.
the thing is, what happens if I just type this? Well, this is this is integer, and this is a double.
Yeah.
So which one of these does it pick, right? That's really not clear. And if you look at the...
But I think in this case, the compiler would probably complain. I'm not super sure about this. This is why templates are kind of nice, because if you used templates for this, the templates would tell you, hey, I deduced a type called integer, but I cannot cast the other argument implicitly to an integer. So you have to be more explicit. So templates with type deduction, they allow you to skip the template parameter, but use it if it's needed. So again, it doesn't really tell the whole story, this example.
Standard, it actually, you know, defines which one it is. The problem is most people aren't going to know that, and even if you do know that, it's not super obvious.
With templates, the compiler will check this for you.
Therefore, it might run the wrong one. You might think this run the float one when it's really run the integer one, and if this is, say, 0.3, this is actually not doing anything now because it's adding 0 to 4, and you might have a bug here just because of clarity. So therefore, why is it not better to just put an F here, right? And now it is a float version of...
Interestingly, C will make this error. In C, you have a lot of float functions. There are versions without suffix, and if you use this one and pass a float, it will upcast it. So you will have, so the floating point accuracy will suffer. I mean, it will use double, which is a wider type, but it will introduce gaps between, for example, subsequent epsilon float. It can be a problem. I encountered this problem at least once.
And you can immediately see that you get a warning if you're doing something wrong, and you know, the compiler will be a little bit more annoying maybe, but it's so much more clear. You won't accidentally do anything, and you know, it's typing one more character for a little bit of clarity, and not spending an hour, or maybe if you're unlucky, days looking for that bug. That is a really good thing. You're saving a lot of time. So again, be explicit. Don't try to hide things. If you're trying to hide things, you're probably setting yourself up for problems later on. And here's
items.
something that I did. I worked on a project a long time ago with JavaScript. And JavaScript, you don't have to define.
So the reason that the C approach, at least, I mean, if you're using templates, you don't have this issue. But if you use this in C, the reason you can catch this error because you have redundancy in your program. You specify types in two different places. The variables have types, and the function that you are calling also has types. So the compiler can see that, hey, there is a mismatch here. It doesn't know which is the correct one, but it sees that at least two of them disagree. And redundancy is it's used in a lot of places in programming languages to avoid mistakes. But if the syntax is compact and it's very kind of clean, like it doesn't have too much noise caused by the language, being terse is not a big issue.
Define things, right? So you can basically do this. I have an object and I just add dot hello and then I, assign X to that. Great, and then I want to read out that, except now I use a capital H. Now I don't get any kind of error from this. What I will get is 0 because hello will now be defined and it will be set to default 0 and X will be 0.
I think he's talking about JavaScript. Okay, JavaScript.
X out. Now I don't get an error.
Yeah, I think JavaScript will just tell you undefined.
I don't get, anything complaining. It just doesn't work. And I can tell you, I wasn't actually the one writing this code, but we spent a good day looking for this problem, which is a super small typo. And, people tend to complain in C that you have to declare everything and you have to write everything, many, many times. And yes, you do. But actually having it defined once and then have the compiler check if everything is, correct is a really good thing, because writing that type def, that might take you 20-30 seconds, but looking for a bug all day will drive you nuts. So again, more code is good. More explicit is good. Crashes are also good. So, if you're a user of software, crashing, is bad. You don't want software to crash. So people tend to think that, if we can somehow automatically make software not crash, that would make the software better. Well, if you have a mistake in the code, you want that mistake to actually be visible. And if it's not, if you throw some secret warning somewhere or jumps out to an exception or handles it gracefully, it's much less likely that you will actually fix it. So
I kind of disagree with the author on this.
therefore, you want crashes to be
let's listen
wrong.
to
You
till the
want
end.
crashes to ruin your day, because that will force you to fix them. If you have an application that has a bunch of bugs in it, you ship it to somebody and it keeps crashing, they'll complain. Whereas if it secretly doesn't do what you want and corrupts your data maybe a little bit, but not very visibly, and then puts an error message in some file that nobody ever opens, well, then you have a really bad thing, except nobody knows why. And and then you have a debugger, and debuggers, when you crash, they stop and they say, here is where the thing went wrong. And that means that you can look at that, and 9 out of 10 times it's really freaking obvious what went wrong. So when it happens, you usually fix it. Even if you're not working on that particular part of the code, or you're doing something else, it's really, really good to try to fix the bug when they pop up, and crashes help you that. And this brings me to another point, which is, I don't think a language should be complex. I think a language should be as simple as possible. And then
Okay, about crashing, there is this approach for writing programs that whenever any of the assumptions about the code, often encoded as assertions, turns out to be false, we immediately bail out, crash the program, print the stack trace, dump the variables, create a crash report. It works fine for development, but not when you actually want to use the software. Users of the software are probably more important at this point, and they tend to have data in the program. So warning the user but keeping the program running is sometimes more important in this case. So not crashing, but alerting. This is why we have different release build modes, build variants when we build software. There is typically a debug variant. There is so debug variant has like the most debug information. This is where you can run debugger and have access to everything. There is some optimized debug version, which is reasonably fast and checks all of the assertions and crashes whenever any of the assertions is false. And there is a release build. A release build, when it detects that some of the assertions are broken, it tries to recover, it tries to continue. Because this is what the user probably needs. The user probably needs to be able to save the data. So it's good to have a header like build variant that can tell you, that can give you compile time constant, whether you are building in debug, release, on this, or this in the middle, in between mode. And only crash if you are in not release. I can even say yeah. Okay.
Then you should do complex things with it. And if you want to do something more complex, build a cool tool that does that for you. So tools are really good. Have a simple language and then make a kick-ass tools that makes it easier. So, you can do, completion and all kinds of fun stuff in an editor that helps you type. And then that alleviates the fact that you have more code and needs to type more. So that to me is a much, much better solution. And if you look at C, it actually has the most mature tools of any language. And that's just because
Yeah,
the language is
absolutely.
so goddamn simple.
Whatever language you write, you probably, when you want to produce a library, you typically export it as a C library.
So
It's
in fact, I have my own debugger, which I put.
the C libraries became a sort of intermediate dialect between software.
Posted on YouTube. You can check that out because I can basically write my own parser of C and do cool stuff. Like one other thing I can show you is hold on.
But parsing C and doing stuff with this. So C is often used as a target for other languages. Other languages often compile into C, but I haven't really seen C being used as an input. So as an input to some analysis or some tooling. This is rather rare, I think.
.org. Let's see if I have my website up. Yeah, so here is a website that I have, and this website is a website for all my source code. So you can check all the functions, all my libraries, blah blah blah, read all the stuff. So how was this created? Well, it was created because I needed it. So I wrote a little program that basically parses C code and reads all the comments and puts together a website. And that means that if you, for instance, now look inside my source code, I'm just going to take a random file here. So Forge is one of my libraries. You can see that each function here has a comment on it. And then if I go into my documentation and look up a function like say rand_i, you can see it has a description here that has been copied from the file. Now, this means, you know, to implement this, I had to write a C parser. This is kind of a simple C parser, but that's actually doable because C is a simple language. So this is basically a way that I do all my documentation, but I do it in sort of a simple way, using my own tool. So that's a great example of where I think like you can do a lot with tools, but if the underlying thing you're writing tool for is really complex, then you're much less likely to write cool tools. So we'll talk about that a little bit more in a second. Let me find my slides. There we go. Okay. So next comes naming. So I think
This is nice. This is actually pretty cool. The fact that C has simple grammar, you can parse it and you can actually put some stuff in there. It's not unique to C. I would say most languages can be parsed easily because most languages, source code is just a piece of text. You just scan the piece of text for a token that you need, you extract the token, so you have the data. I don't think the simplicity of C is really an argument, like pro or against anything. You can put those special tokens in comments in literally any language, and you can extract comments from literally any language. It's not like one of them is significantly harder than the other.
think, and a friend of mine used to joke that really wide code is good code. You can measure how good code is by how wide it is, and sometimes we joke and say like, oh, that's really cool, that must be some wide ass code running on that, basically. And why is wide? Why is wide good? Because wide means you have long names, and long names means you're descriptive, and the more descriptive you are, the better. And I think that C programmers in general are quite bad at this, and I think actually all programmers are bad at this, but C programmers sometimes are worse at it. And again, people don't want to type, and I think that's wrong. Be descriptive. So here's how I name things. So I define, all my defines are with capitals, with underscore as spaces. My types are, you know, capital, small letter, and I capitalize every letter, no underscores. My functions are like this. This I don't do. This is another way of doing functions. Sometimes I think this is better, and all my code is in this style, but
I would say the main style of the author, I mean, is the one I would prefer, because the one hard thing about camel casing is that when you have acronyms in names, it's always so weird to spell, for example, GPU, UI. No, those short names, where actually every letter stands for a full word, are hard to put together. And when you have multiple of them, and then some other name, it becomes less readable, like GPU manager. So we have GPU M manager. Underscores would be nice. Actually, names with underscores and capital variables would be nice. It's like the best of both worlds.
I actually think this is a really good style as well. So I don't want to, even though I don't do it, I think it's really good.
I'm using this style mostly because I just went for Google style. Google has Google and different companies, they are publishing those style guides that developers internally use, and they are also good general practices that make code consistent in general. I'm following the Google style guide because I'm also using a lot of Google libraries like Skia, and eventually there will be more of them.
Can be confused with a variable, which is this, whereas this can be confused with a type, which is this. A lot of people don't do the first one capitalized on functions, which can make it easier to see that this is a function and this is a type. I'm not sure about that. I think that functions are fairly easy to see because they have obviously parameters. But just doing this shows really clearly what is a type and what's a function, and it becomes very clear just by looking at like the formatting what something is. Second, I want to say that spacing matters. So some people use this, that's how I do it, and some people use this where they have a little space here. I think this is horrendously ugly. That's obviously only an aesthetic, opinion, so obviously, you can have a different opinion, but I do think it's really, really important to not mix the two. And the reason for that is if you have this function and then you have this function, which is named something else, if I now search for this function, I will also get this function. But if I search for this and I add the parentheses here, the first parentheses, then I won't get any of these. But if somebody is using this function somewhere, but they have a space here, then that won't show up. And that's really annoying because, if I'm looking for where is somebody calling this function, I want to be able to search for this function everywhere without accidentally searching for this one. So that's why I'm saying that, like, it is, I guess, acceptable to do this, even though it's ugly. It is not acceptable to mix the two.
Regex will solve this.
Bad idea. The same goes with spaces here. So here I'm actually have better reasons why I think you should have spaces. So this is legal C, where you don't have any spaces. This to me is much prettier. It's wider and gives it more air. But there's actually, you could say that this is only an aesthetic difference, but in my opinion, these are actually not as good as these ones. And the reason is, let's say I want to search for every time I assign A, right? So then I can search for this, where I assign A and then space and then equal and then space again. And then I will actually get this line. If I remove that.
So this is why most programs, like IDEs, when you search, they have this button for use regular expressions. And if I'm looking for all instances of timeline, but not TimelineWidget, I can put a word boundary here. And now it won't find any widgets. If I just remove one letter, it will not match it anymore.
And search for only A equals, I will actually hit this one and that one, and I don't want that. I want to only hit this one. Now, obviously, if I assign it with plus equal, I won't find that. So, it's not waterproof, but it's still better. And that's why I think that actually having this space here is a good idea, because it separates things. And then actually in C, you can do like fucked up things. You can do like this is legal C. And what this actually means is this. Whoops. This. But nobody can read this, even though it's totally legal, so nobody should ever write that. That's just like stupid. If you're writing this, you're showing.
Okay, the fact that you can abuse a language feature is not an argument against a language feature.
Showing off, and you're not supposed to show off when you write code like that. So other things I do is I reuse a lot of naming, and when I do coding, I tend to come up with names and then stick to them. So here's a few definitions that I use. I use type as part of an enum. I use arrays for arrays, obviously. Nodes are things that link to each other. They're not the same as a linked list, which is a list. An entity is a generic network thing that's obviously used in games a lot. Handles of different kinds are usually opaque pointers to structures. Func is something I add as a postfix to a lot of functions that are meant to be used as function pointers. So if you have a function that takes a function pointer, the function I give to that is usually called a something something underscore func, just to say that, oh, this thing isn't being called directly, it's being used as a function pointer. Internal is something I use for a function that should not be called outside of a module or something like that, or a .h file. And then I use a lot of words like these ones, like count and length and found and next and previous and array and things like that. And I use them the same time every time. So if you ever find an I, it's an integer. I, j, and k are always integers, and they're always used as counters for things like for loops. F is always a float, never anything else. So that means that when I see an F in my code, sometimes I have an F and an F2 and an F3. Those are temporary variables that I know are floats, and I can never accidentally use them as integers because I use the same names everywhere. And that creates a lot of familiarity with your code. So you can look at code that you wrote a long time ago and be like, oh, I get this. I'm not using a bunch of weird names and that I have to figure out. So that's really useful. I also think that actually long functions are good. And this is another controversial thing, because there's actually like computer science people that teach that you should never have a function with more than 5 lines of code, which to me is just moronic. Sequential code is really easy to read, right? That's how we read books. We read from the top.
Actually, the longer function, the better for me. And
your own adventure book where you have to
the longer I code, the more I think there is no limit actually to this statement.
That's actually, you know, much harder. And
of course, the limit is only when you have code repetition. When you have code repetition or code reuse, probably good to actually introduce functions, but it gives you a really nice linear overview of how the program works at a first glance. You take a look at a single, huge function that does everything, and by going through this function, you can see how the program is initialized, what is the main loop, how the shutdown routine works. It still has to call some functions because eventually there is some... actually functions are not really necessary. They're only necessary if you have recursive algorithms anywhere. And even then you can probably often replace them with stacks or queues. So almost all programs can be written without functions.
And the other thing is, I like writing code that does something. And a lot of people, if you have a lot of functions for things, people tend to write a lot of functions or things that handle other code. So if you see that you have a lot of your code be called things like something something manager, or your something something controller, or something something handler, you're probably not writing code that does something. You're writing code that handles other pieces of code. And I think that's like a warning flag, because it's really hard for someone coming from the outside, like, knowing what that handler actually does. Or if it's a function that is like clearly assigned as this function does this thing, then it's much clearer what's going on. So I have some like horrifically long functions. I'm going to start another copy of Visual Studio just to show you an example of a very long function call and why that's actually a good thing. So I'm going to show you a bit of source code from Love. Whoops, I clicked the wrong one. Hold on. And while I wait to do this, I can actually say that I saw John Carmack actually tweeted about the Gripen, which is a Swedish fighter jet, and that control code that controls the plane, because it's a fly-by-wire plane, basically has one main loop and that main loop calls a bunch of functions, and those functions then never call any other functions. You have only one level of indirection, basically.
Yep.
And he said that once they certified that code, 20 years later, they still haven't found a single bug because it's so clear. You're not doing anything. You're not hiding anything from somewhere else. So that's why I think actually people should be way more receptive to having long code. So the function I want to show is called something, and it's in this mega function here. I'm gonna see if I can make it slightly bigger, and it's over 1,000 lines long. So this is my main rendering loop for my game Love, and it's this like mega function. It starts here and it's called ME draw graphics, and then it just like keeps going forever.
Yeah.
And it goes through every state of everything that needs to be drawn in the game, and it keeps going. And
Even if you don't inline stuff yourself, the compiler will do
Yeah.
this when compiling the program.
frame. And why is this good? Well, for instance, here I enable blend, and then I can just like follow here and see is blend enable, and just like know what the state is, and I can go up and down. It's really easy to see that like, oh yes, because I disabled blend here because I needed to do something, and then I need to enable blend because I need this blend mode. And that means that I keep track of the state at any one time, and I can very easily sequentially read this and know exactly what happens. I know exactly where I am in the code and what's going on, and it's never like ambiguity about things. I have obviously some functions here that do things, but they're kind of isolated. So this is also, I guess, a function of OpenGL, which is a little bit annoying because you can get a lot of state leaks. But here I just like always know where I am in the code because it always runs sequentially. So long functions are usually really good in my opinion.
So his example was, it didn't look super readable because of verbosity. You didn't just had a lot of interesting stuff on screen at the same time. But this approach still works nicely. You can always have some folding. Yeah. So you don't really need to see all of this if you're not interested. It's good to annotate those blocks with comments, what you're doing in a block. But yeah.
Talk about naming some more. So here.
So this is just a C of naming convention. You usually, in C, because C doesn't have namespaces, you need to kind of manually add a namespace prefix to every symbol name in a program.
We have a bunch of functions, and this is how most people name their things. Like, I want to create an object, I want to destroy an object, I want to move an object, right? I think this is bad. This, however, is worse. Now we have create and remove and move. Why is this worse? Well, because the opposite of create is destroy, not remove, right? If you have the opposite of remove, might be add, which is actually also bad because the opposite of add would be subtract. So that's bad naming, basically. So you definitely want to go with create and destroy, or words that basically equal each other. What's much better is actually called object create. Now, if you look at this code, you can see that this looks really irregular, whereas this looks much more regular. And if you think about it,
But it looks more regular because it's aligned. It's aligned to a column. And it doesn't use different prefixes for some reason.
Is basically like a directory structure, right? You start with, I have an object, I do something with that object, right? Here is like, I do something with a thing. Well, it's much easier if you start with the thing you're doing. And even better is to do this, where you have, I have a module, and in that module, I have an object, and in that object, I can create, right? So now I've created this like structure where I can really easily find where things are. So let's actually show some examples of this. So I'm going to go into Stellar, which is the application I'm working on right now, and we're going to look at some...
So the code I'm moving into TimelineWidget, just as is.
I have Imagine, for instance. So this is a
Each of those will have to be fixed individually.
API that I
Going to be a lot of
And
work.
as you can see, every function here starts with imagine. And that means that anytime I see this, I know exactly, oh, that comes from that module, right? It's always clear where this resides. And then you can see the second word is library, right? So these are functions that deal with libraries, right? And then you can actually see that if you check my, let's see where we can find the actual files for this. Here we go. There's actually, the files are actually called I_library. So even if I, if I find this one, not only do I know that it's in Imagine, I know which file it's in, right? And then we have a bunch of functions here to create interfaces for loading DLLs. So all of those are called
I hear that a lot of the reasons that Eskil likes C is that it's easy to do textual patterns. It's easy to match it to like text search queries. It's happening here, but I think there were like two different examples where he said that it's convenient because I can easily, text search for it.
Interface, right? And then we have interface destroy, interface register, we have create, count, list, and then get by number, get by name, and then we have load, which isn't part of the interface, so that doesn't have the name interface, and then we have unload to unload a library. So this very clearly shows like it's like a directory structure, and it becomes really easy to find what things are supposed to be named and where they belong. And you can see here's another function. It's called imagine mutex because it's all about the mutacies. And then you have, all the imagine settings functions and so on. It becomes very, very clear. Again, these names are really long, but they're also very clear because of it. So that is like really good programming in my opinion.
Okay, that was a very controversial statement. Those things are probably easier to manage if they are attached to objects. You cannot call module object move on anything, only on objects from the module. So attaching a function to an object makes sense. It makes the code easier to parse. You can invoke it more quickly from the given an object. I guess it gets object argument as the first argument. And create and destroy, in many languages, those are not even separate functions. Those are constructors and destructors, and they are invoked automatically. So you don't even have to think about them. They are just handled.
Oh, relinquish is another example I could have shown, but pretty much all of them are. So let's talk about API design. How do you design an API in C? I start from the outside usually, which means I create the actual API that I want, and then I sort of fill in the functions behind the scenes. So I start with what is the interface to talk to those things. And that is really smart because if you have an interface you really like, that can actually have multiple types of implementations on the inside. And you can change how it actually operates on the inside without changing the interface. And that is really, really useful if you want your code to live for a long time, which you usually do. So let's have a look at that. Here again are my naming. I tend to name my functions like this, my files. So this is seduce, which is my library for doing UI. So then I have obviously seduce.h. Seduce.h is a external file. A lot of people have like one file. Maybe I have an example of that. No, I don't. So a lot of people write something like this. They have text.c, and then obviously you need text.h, right? The problem with this is nobody knows what anything belongs to, right? Text.c may need some other files, and you don't quite know what it needs. And you end up with a crap ton of .h files. So your top of your files will just have like loads and loads of includes. And that to me is like, that's really bad. So here we have seduce. we only have one .h file that has loads and loads of functionality in it that are defined in the C files. So if we actually, hold on, we'll look at...
I think this granular splitting only happens if your project is very large and you care about compilation speed. Doesn't really change much, anything really.
Project with real code. So seduce is this big. So it's like 30 files or something. They're all called...
So Clang has those nice utilities that can actually include what you use. So if it notices that you're including a file that you don't need, it will give you a warning. And if you are not including something that you should include, you can ask it to add the include. Like, VS Code has integration with CLangD, so it works here nicely.
Called s underscore, and if we then go to actually seduce, here we go, this is seduce.h. You can see this .h file has loads of functionality in it, and that resides in all those 30 files. So this is the external interface that you need to...
External interface should always be ideally a single file.
If it's part of my UI code, you know it lives in this one.
Except maybe if you have some platform-specific stuff, maybe then.
And also, if you look at here, I actually put all the seduce files in this folder, but the actual seduce.h I put outside so that when I work in another folder with, you know, an application, I always have access to this module from this .h file. So it makes it easy, sort of UI-wise, to access the file you want, sort of the functionality you want. Okay. So one thing you might find here is I have an internal .h file. So sometimes you may have a structure or something that you want to communicate within this module that isn't external. So the external shouldn't know about that. So then I tend to name those internal, just to sort of say this is .h file, but it's not something you should look into because it's basically just for internal things. So let's talk about object orientation. Object orientation is something that people think you cannot do in C because it's not an object-oriented language.
Who thinks that?
But I find that object orientation is very straightforward in C. And in fact, I think it's better in C than other languages because other languages tries to fool you into thinking there is such a thing as object orientation in computers where it really isn't. It tries to tell you that there's, you know, something that has both code and data in it. And that's actually not true at all. Code and data are separate. In fact, on modern CPUs and modern operating systems, it's required to be separate because data is stored in a read-write able memory, whereas code is in execute only.
It depends. It's not exactly like that. Of course, code is executable because code is writable. It has to be loaded into memory somehow. And it's also possible to write programs that will execute itself, that will kind of rewrite their own code. They're called polymorphic programs. And it really depends how you map memory. And that's it. Some operating systems like Android tend to forbid it. So they have this write XOR execute facility where you can either modify the memory as a piece of text, read write, or modify the memory, modify or execute it.
And you can't read it.
It's not both at the same time.
And that's to stop a lot of like malicious attacks so that you can't trash your memory and then have the CPU read that as code and do bad things. So therefore you basically write protect all the memory that can run. So code memory.
It's very rare to interleave code and data. Usually when you exploit something, you are just jumping to a different part of code and not writing your own instructions from scratch.
Memory can either be run or it can be changed. And that's sort of a security things that, exist everywhere. So objects are just fundamentally wrong. So if you have a programming language that object oriented, you might recognize this, right? You have a thing, you create an object, and then you do something with that. Well, actually in C, you can make something just as simple. You do an object create, which is a function that returns a handle. And then you can just have a function that takes that handle. And then maybe, if you want to do something more, you can, add any parameters you want after that. This to me is actually clear. It says that it's a function, it's a piece of code that does something on a piece of data. And this is also a little bit nice for other reasons. Like for instance, you may have a function that takes more than one object to do something with it, like transfer data or something like that. And then it sort of just proves that one object is not, worth more than the other. It's not one object calling the other object. It's a function using two objects. So to me, that's much more clear. And void pointers are really your friend here. I think there's a slide showing you how. Oh, no, it's not. So I'll actually show you. So I'm going to show you an example of a library that I have called Testify. So Testify is a library that does storage of binary data, and you can set up a handle and then send data to it. So let's take a look at how I've implemented this API, and you'll get an idea for why void pointers are really neat. So here's a function called Testify Network Stream. Obviously that's, it lives in Testify, and it's a networking thing. And
I guess this is crossing the limit of wide code, where you can't really see what's out of the screen.
It's stream, whereas over here we have datagram, which is for UDP, and this is for TCP. And then we have address create. So this is a long ass name, and you give it some parameters, and it outputs a handle. And if we look at that handle somewhere, oh, it's in internal, that's actually a void pointer. And that means that it's not defined here. All we say is that this thing basically gives you a handle, and here it's, here it requires a handle. So for instance, if you want to tell the stream send everything, I want to force it to send, you just give it, the handle, and then you go. The application itself that is using this API has no idea what this is. It's just a pointer to something. It's a void pointer. You can't read to it, you can't write to it, you can't do anything with it except give it to all the functions here, right? So we've created something like that is opaque. Now, if we go into the actual implementation of this, we'll find that there is a t_internal that looks like this, that actually has a bunch of stuff in it. So here's all the buffers and everything, and this is t_handle. So this is the definition of a handle, but this is not shared with the outside world. This is what the actual functions are using internally. And if the user were to change any of these values, they may fuck something up. They may, crash the computer, do bad things. So we don't want the user to do that. We don't want them to have direct access to any of these memories. We just want to give them a pointer. And therefore, we define all our external functions to have this void pointer. And I do this all over. So if we go into my rendering library, which might be a better example actually, you'll find, for instance, here a bunch of shader functions, and they all have this, R shader. And I think R shader is defined here. So here, R shader is just defined as a void. So basically, it's a pointer to nothing. But then, of course, if we go into our internal thing, we have R shader that obviously has lots of stuff in it. But this is internal to the module, and the user of this library will never know, and they shouldn't know. And that means I can re-implement this a million times if there's new features that I want to add, and I don't have to change anything in the external applications. So good stuff. Let's move on. Let's talk about macros. I don't like macros. I think macros are generally bad. They have a little whiff of C++ in them because you can basically shoot yourself. But they do have a few useful...
Macros have gotten better over the time. With language servers, so, macros can be used more easily now.
There's one thing where you actually want to write, you want to duplicate a lot of code for different types. So if I write a a loop that looks like, say, this. I want to write float. Sorry, I'm gonna write a func that takes array a. Let's call it that, and that is a float. And then I'll to float. I can't spell today. And then we do another one, array b, and then we'll do a uint count. By the way, I only use unsigned integers. Like, that's my default use. Int is only used when I actually have something that can be negative. That's just the thing for me. So
it can lead to problems. On modern compilers, the overflow and underflow, actually no, for unsigned it's probably well defined. But if a compiler detects that some value of an unsigned integer goes below 0, it may assume that it's not possible. And it may eliminate a whole code branch based on this assumption by propagating back, the fact that it cannot happen. It can make some changes in the program.
so here's uint I.
It can mess you up, and it's one of those terrible things that happens only at high optimization levels. At low optimizations, things will run fine. At high optimization, program will start crashing.
For loop.
And for that reason, using integers with sign is typically safer, because you can safely subtract for them something that will temporarily go below 0 and then go back above 0. Even if the code is the same, the compiler can treat it differently.
I is equal to 0, I is less than count, I plus plus, and then I don't know what we're gonna do. We're gonna do array, say times equal. Whoops, we need some brackets.
I'm not sure if this is
like this.
such a clever code. You should probably use static cast.
I'll fight over who reports them first. Oh, sorry.
Whatever.
A and B. See, I found them too. Okay, so if we have this function, this is lovely, easy function. Except now I want another version of this that doesn't take a float and another float. I want to take a float and a double, and then I want another one that is a double and a float, and then I want another one that is an int and a float, and then I want another that is a short and a float, and then I want another that is an int and a short, and you keep going. And now you have a million different versions of this, and you want to build, say, a switch case thing that has every one of these different combinations, because basically you want to be able to, multiply together all these different types of every conceivable type. Well, then actually making this into a macro and then replace this and this as parameters to that macro makes sense. That is a super rare thing, so don't do that unless you really have to. If you actually typing it out might not be so bad. The advantage of doing this is obviously if you can make this work, you won't create typos in all the versions. So you might not have an easy way to test every combination of these, but if you can test one and then be sure to use the same code over and over, you may have less, problems. The problem obviously is as soon as you use a macro for something like this, all your error message will be totally screwed up, all the line numbering and all that stuff, and the debugger will not give you any kind of reasonable things because, let's face it.
Yeah, and this is what was fixed. So it was the case that if there was a bug in a macro, debugging this was hell. But now when you have even a complex macro, the compiler will usually tell you how it's expanded. If I type something like that, when I hover over the log, the language server can tell me, hey, this log is actually expands to, and this is the expanded macro.
At debugging code.
So it depends what tools you're using.
With the preprocessor. So
but when he recorded it, that was the case.
Really kill you. So don't do that. I read code where people have basically changed this into a macro. So they have a macro called this, define, and then like this, and then they just like do this and say, people who do shit like that, they should just be shot. This is like horrible, because this, nobody has any idea what the hell it does.
Not for not loop, but with for each, and it's a macro like that. Usually don't use it in your day-to-day code, but if you are, for example, on a programming competition, then those macros are very convenient. They usually put more arguments here, not just one, because if you have multiple nested macros, you want to use different variable names. But a for each macro is a very popular thing in competitive programming.
Whereas this is like, you can be a kindergartner and you understand what it does. So yeah, don't do that. Anyhow, so there are two macros that I discovered kind of late, but I love, and that is file and line. There's another one called function, which is not standard, and you shouldn't use it, and it's actually kind of fucked up because this is a preprocessor thing, and the preprocessor doesn't know about function. So even though some compilers have some kind of version of function, and don't use that because it's kind of specific, and yeah, so don't do that. But file and line are really nice, because what they do is they replace this with a with the file name. It's a string, and this with an integer of the line. So what the hell can you use that for? Glorious debugging. So I'm going to show you two different APIs that I have written that uses extensively this. And the first thing I'm going to show you is a memory debugger. And you know, I mentioned earlier how I think that memory leaks are really easy to find, and you're going to understand why in about 10 seconds. So I've created these functions. Here is a version of malloc that takes normal size, but then takes two more arguments. One is file and one is line, right? And then I have a macro here that replaces all the mallocs with fdebug and mem malloc, and then takes whatever input, put that as size, and then adds file and line. Now, what I can do inside of this function is that every time you allocate anything with malloc, I will register the file and line where that was done. And then whenever you free something, I can register where it was freed. And that means I can create this function called, where is it? memprintout, that will actually print out to standard out every allocation I've done, which line, how many times they've been freed, and how many times they've been allocated. And that means that finding debug, memory leaks is absolutely trivial. Now, once I did this, I started loving it. It's so useful for so many things. And since then, I've, done a whole bunch of cool stuff to this. So things I, for instance, do is I over allocate all the allocations, and then I put a magic number right after that, and then I can call this function debug memory, and that will actually go through all of those pieces of memory after my memory allocations and make sure they're intact. And if they're not, I can throw an error. So I can basically say, oh, you accidentally overwrote this piece of memory over here that was allocated in this function. And that is lovely because it means it's very, very easy to find some nasty bugs. I've also added some other things, like for instance a comment. So you can, like, if you allocate something specifically, let's say you have an allocation that happens a lot of times, but you want to be able to keep track of.
It would be nice to have something like that, but not necessarily in your program, but as a sort of protocol with debugger. When I run my program normally, it could run fine. But when I attach debugger, the program could say, hey, if this memory is accessed, I want it to crash. Maybe this is what ASAN does, actually, with its shadow memory.
Which one was these? So then you can easily put a comment on that, and we'll remember that this pointer has a comment, and then I can print that out. So that gives me even more abilities to keep track of what the hell a piece of memory is. So this is just like lovely, and I'm wrapping malloc. I'm realloc, which is really good. I'm gonna talk more about realloc, why I love realloc soon, and then free. So this is like totally great code. I use this at least once a week, just like turn it on, and my code runs a little bit slower, but it's just like it's totally beautiful. And if I actually quit this application, let's see if I can check standard out here. So actually in the application that I showed earlier, no. Huh, okay, I may not have it on. Yeah, it wasn't on. But basically I just push it out in my standard out at the end so I can see like, where my memory leaks are. Or whatever is going on, and it's really, really good to keep track of. It also gives you like a sense of where memory is going, which is a good thing. Then, oh yeah, Testify. So Testify is another library that uses this. So I show you how to do all this, stream address, blah, blah, blah. So this is basically creating a network connection. And then you can also create a file, same handle. You can create a buffer, same handle. But what you do once you have this is you can pack data into it. So this packs an integer, packs all the different types here, floats and strings and all that stuff. And then I can use these corresponding to unpack these. And that means that I can easily pack data into a binary thing and then unpack it in the other end, either if it's a file or if it's a network connection. Now all of that is pretty straightforward, but if you've ever worked with binary files, you know that it's super hard if you do something wrong. Like if you pack 2 integers and then a bunch of floats, and then you read out 3 integers and a bunch of floats, well, now you're offset by by 4 bytes, and everything, all the data is now trashed, and all your data is coming out wrong. And maybe your code will crash, but it'll probably won't crash. It will just like send out a bunch of trash. So you did something wrong somewhere, and at some point it may crash, but you don't know where it broke. So what I do here is for each one of these things, I give it a name. That means you can assign any kind of name describing what the data is. Now that means that when I unpack this, I can check that name. Now you may say, why are you storing name there? That's really slow. Well, normally you don't do that. I have a function called memory debug set that will actually turn this feature on. So everything you pack will now have a little header that says what kind of type and what kind of name does it have, right? So then when you unpack, you will be able to say, hey, you're actually trying to unpack the wrong piece of data. Now that's nice, except you can make it even nicer because this function is actually not a function, it's a macro. And if we go into the internals of this, let's see if I can find it. There is a debug file somewhere around here. Hold on, I think it is.
Speaking of macros, I could use a macro for this pattern where I have to first lock a weak pointer into a strong one and then acquire a mutex to do something. Literally anything. Oh god, there's so much locking going on because I want to use multiple threads.
Here
Whatever.
no. Where is it?
So in Automat, those threads, they lock a lot, but the point of all of this is to decouple those 2 threads so that when one of them is busy for a long time, the others can continue. There is no blocking between them. I mean, locks can introduce blocks, but not here. If I'm careful about not holding the lock for too long.
No, there's a debug file here somewhere. I've hidden it really well. Bum, bum, bum.
The video is quiet right now.
Let's see. Oh, there it is. So this one puts a macro around every function. So, pack has normally three parameters, but then I add 2 more with a file and line. That means I can make super verbose error messages. I can basically say that on line so-and-so in this file, you're trying to read a float called this, But really what's in the data is an integer called this. And that makes it absolutely trivial to find the bugs in, you know, your data. And this is just like, I hated these bugs. I had these bugs like all the time. Anyone who packs data, they're building network protocols, hate this stuff because like debugging, it takes forever. And then I implemented this, and yes, I over-engineered it a bit, but now I never ever have those problems again. And I write a lot of binary files, and I write a lot of network protocol stuff, and it always works 100% because as soon as there's tiniest bit of problem, I get a really good error message, and I can fix it very quickly. So great thing you can do with macros. Okay, let's move away from macros. Let's talk about memory. So this is going to be a very big portion of this talk. I'm going to talk about memory because memory is really what you need to have control over if you're a C programmer. It's the kind of thing that people are trying to hide in other languages, and I think that understanding it, having control over it is a really good thing. And even if you actually don't program C, if you understand how memory works in a computer, it's going to help you so much. So let's talk about memory. So I'm going to try to explain how memory and pointers work. And this you may know, and this may be boring, but I'm going to explain it the way I think about it. And once you think about it the way I think about it, I think you can do some nifty things. So the first concept is to understand that if something exists, it exists somewhere. That means that everything that exists can be described either as what it is, but also be described as where it is. Ah, interesting. So that means
there are some things that don't have a unique address. They have to be specially marked. Like that. I mean, of course you're not going to have a field like that, but it is used for some template metaprogramming magic. There is possible to have compile time entities with no unique address, but that still can be, for example, compared with other things.
That everything in memory is essentially all your memory in your computer can be set as one very big long array of bytes. It's a bunch of bytes, just right? And that means they're all numbered. You have a number going from 0, which would be the first byte, all the way to, well, how many bytes you have in your computer. And that is basically a pointer. Each one is numbered, and therefore you can reference a piece of memory with a number. Think of it as street addresses, right? If you every house has a number, and if you know that number, you can go to that house. You don't have to know what the house is. If you know the number of the house, you can get there. If you're trying to go to number 11 and you're at number 9, you know that you have to go 2 more houses down to find the house. That is very simple, and that is really all that pointers are. So obviously, pointers have some interesting features. They have something called a type. So why do we have types? You could think of pointers as just a position, but in order to be a little bit smart, we actually type our pointers. So a pointer is just pointing to memory, and memory doesn't know what type it is, but it's really good to know what type it is. So you may have a pointer that points to an integer. It's good to know that that is an integer because that means you can read the data. If you don't know what you're pointing to, you can't pick it out of memory because you don't know how much memory. You don't know what to do with it. That's why pointers are really important. So here we have a couple of pointers. A void pointer is basically a pointer that we don't know what it's pointing to. And sometimes that's a really good thing because we may not want to tell anybody what we're pointing to. I showed you that before with my handles. That's a good use for void pointers. Void pointers are really useful. But normally you don't want to use void pointers because, again, clarity. If you can't say and the user should know what a thing is, then don't use a void pointer. Here are two pointers. One is to a short and one is to an integer. Shorts on a normal modern computer is usually 16 bits, so 2 bytes. An integer is usually 4 bytes. So if you take a pointer p, which is our void pointer, and you copy it to this and that, they actually point to the exact same piece of memory. But here, when we take that and we copy out of it, actually it should be a star in front of this. Basically, we're saying, give me what this points to. This function, this will grab 2 bytes, whereas this will grab 4 bytes. That will grab them from the same place, but this will grab more. Okay, so what does this mean? This means that if we then move forward with our pointers, we basically, walk one address up, we add different amounts. Since this is our short pointer, we add 2 bytes to our pointer. And this one, we add 4 bytes to our pointer because we have the thing. So the analogy I would say is like, let's say you're outside of an address of a house. You need to know how big that house is in order to know how many steps to take to be at the next house, right? That makes sense. So knowing the type of the pointer allows you to walk to your neighbor, right? And this is a really clever thing, right? If you think about it, if I give you my address to my house, I automatically give you the address to my neighbor. All you have to do is just, add 1 to my address, and all of a sudden you have the neighbor's address. And that means that pointers are pointing to one thing, but they're also kind of pointing to the next thing, and the next thing, and the next thing, and you can go on forever. And that means that pointers are also arrays, if you think about it, right? It's like pointing to a house on a street is really just pointing to a point on the street and pointing to the whole street, right? It's just like a handle to a starting point of a street. And from that starting point, you can actually go forward and actually backwards. You can obviously walk too far and, end up in an ocean, which is bad. But the concept that a pointer contains just one thing is wrong. It's multiple things because it's an array. So yeah, here I just show you basically that if we, even if short and int was the same thing, we add 1 to this and we add 1 to this, they're no longer the same because we've added different amounts because they're differently typed. So let's move on. Let's talk about malloc. So malloc is the thing you allocate memory with in C, obviously. And I like, in order to allocate, you have to use usually size of. So size of is not a function. It's actually part of the language, and it gives you the size of, a type. So this is how people are taught in school how to use size of, which is size of and then parentheses and a type. And that kind of looks like a function, right? This kind of looks like a function. So people tend to think this is a function. Obviously, it's not a function because this is not a variable. This is a type, so it can't be a function. It's actually much better to look at it like this, as size of, and this is a cast, right? So normally we do that, maybe. This is casting a as a float, right? So think of it as a cast, not as a function. That's the first thing. But that also means you can do some nifty things. So instead of putting float here, you can actually put a value and then put a star in front of it. And by using the star, you're basically saying, I want the size of whatever a is pointing at, right? And what is a pointing at? Well, it's pointing at doubles. And this code is now, if we look at this example, you can actually notice that, wait a minute, we have a double, and doubles are 8 bytes long, but we're only allocating a float. So this will actually do something bad, right? We're not allocating enough memory to actually store a double in this. Here, we're allocating whatever size of a is, which means that this code will actually work, disregarding of what this type is. So if I change this to int, or say, if I have float here. Now, if this code, this will work, right? Because we're allocating a float and we're putting in a float. This takes the type of a, which is a float, and allocates it, and it's fine. Sorry, I just did time 10 there. Don't need that. So these are now exactly the same, right? These are doing the exact same thing. The only difference is that if I change this to double, this code breaks, this code does not break. That's why this code is superior to that code, right? That's why I tend to write my floats like this. Sometimes I don't, because sometimes a doesn't exist. Maybe I have a function that returns a void pointer or something like that. So I may not have a, but if I do have, you know, a type, or a variable, a pointer to that type, I use that instead. This is much, much better. So I almost never see anyone do this, because this is kind of the prevailing way of writing C, but I much, much more prefer this one. Okay, yes, so we actually covered this. I was ahead of myself here. So let's talk about like arrays. Arrays are basically taking a pointer and then stepping forward a bit and then reading out what's there. So this is basically saying, take X, take the address you are, walk 3 steps forward, and then read out whatever's there. And if you look at this code, you can actually see that, you know, this is equivalent to this. So we have, you know, a pointer to uint8, which happens to be bytes, and I copy X to this pointer, and then I take the pointer and I move forward the size of X, which happens to be 1, 3 times. And then I read out what the new X is and put that into A, right? So it's kind of a way of stepping forward, and the size of is really important, obviously, because that basically just multiplies with this. And that also makes sense to, like, some people think that the
So instead of having a comment that says
array should be 1,
it should be locked,
0.
we'll
And
just
that becomes very clear if you think about it as like, how many
locked.
steps forward do I take? Well, 0 is, you know, don't take any steps forward, be where you are, and just like stay there and read out the data. Whereas if you add this, it's basically saying go 3 steps forward and then read out data. So that's why I think that you should definitely, yeah, think about it as addresses in terms of a street. That's a good way of thinking about it. You can also use pointers for funny things like a counter. So let's have a look at this piece of data here. So this code you probably recognize. It's a for loop. It goes, you know, 10 values forward, and it fills out an array with zeros, right? This is like 101 kind of code. Well, you can actually write the exact same thing like this. So here we basically say we take a pointer and we say the end is, you know, this pointer that I have 10 steps forward, right? And as long as I'm not at the end, keep going. And every time I go, you know, increment this pointer 1 step forward and write to the current pointer 0. So this code is actually equivalent to that code. This code may actually be faster because I don't have to do multiplication here. So this is actually a multiplication because what's going on inside of this is that.
So a CPU can, at least on x86, a CPU can multiply implicitly as part of the memory load operation. It can multiply only by small numbers, like 2, 4, or 8. Or if the compiler is very clever, also by 9 and 7, 5. It's a very weird thing, but those indexes, usually they don't require the compiler to multiply, as long as your data types are small enough, and this is the case here.
The computer does pointer plus size of pointer.
For large objects,
Is around this.
yeah, but for large objects, the multiplication is not going to be the problem.
That's actually what the computer is doing here. And here it doesn't have to do a multiplication, right? It does a single multiplication 1.
Yeah, the computer doesn't do a multiplication here. When an instruction, memory load instruction in x86 can take an base address, an offset, and a multiplier to the offset. And this multiplier is, like I said, can go up to 8.
And then just like keeps going. So this is actually faster than this. Now
it's clear he didn't measure this actually. If he did, there is probably no difference.
nowadays we have really smart compilers, and really smart compiler might act.
This one could be faster because it accesses memory in an increasing order, And I guess Prefetcher could probably optimize for this.
Actually, you know, be able to optimize this. But this is actually really good to understand. Like now you're starting to understand how magical pointers are and how nice they are and all the things you can do with them. So let's move forward. Let's talk about structs. So what are structs? Structs are not, as some people think, because they are in other languages, something magical that like the computer actually knows what the name and things are and they do lookups. When you compile C code, all the names or everything disappear. All that a struct is a bunch of offsets and a size. So it basically says that this has, you know, this amount of size and this thing is this far into this piece of memory, right? That's all you need to know. So you can actually get the offset out of something, and here's a bit of scary code, but I can actually get the offset of size by simply taking a null pointer. So we start at the address 0 and we say, let's assume that this address 0 points to the structure, right? So now we have a pointer to the structure that is at address 0, right? And then we say, from that, go to size, right? So now we're jumping forward in memory to find wherever this size thing is. And then we say, now that we have size, use AND to actually figure out what this
A very fun
address
technique.
is. What
I love it.
address am I if I'm standing on a size
It can be abused
in
so
a
much.
structure that lies on address 0, right? So now
But
I get an
it kind of goes
and then I say,
against
oh, I'm going to cast
against quote unquote being clever, which Eskil mentioned he's against.
that
I mean, using offsets into structs, it's absolutely valid. But it will be surprising to many programmers. You can use it to implement all sorts of tricks, like list as a member. So you can have a big structure which contains many variables, and one of those variables can be a list that holds the object, this bigger object. And you can do this because you can find offsets. So from the offset of a list member, you can jump back to the start of the object.
address to an integer. And then I want to read that out. So what I will actually get here is where in memory, how many bytes in does this? And that's a way to sort of, oh, that should be a semicolon. That's actually a way to sort of figure out where things are. And once you start understanding this, you can do some nifty things. Let me show you some examples. Here's another thing you can do if you start understanding memory. So I'm going to show you a way to do sort of object-oriented inheritance. So here we have a enum which says I want to be able to store in a struct an integer or a float. I don't know which one, but I want to be able to do this. So what I'm going to store is I want to name this value. So I want to store a name, and then I want to store a type, right? So this thing I'm going to store is either going to be an integer or float. I always add another one here, which is count, which just makes sense because if you ever want to know how many things are in this enum, you always have a count one. So this will be 0, this will be 1, and this will be 2. And therefore I know how many different types do I have? MST count, right? And the reason I name it MST is because the structure is called my struct type MST. So that means that I can actually know that this value lives inside of this enum and not somewhere else. So that's another little sort of naming thing that just groups all these together and I know where they are. Okay, so anyhow, here is my header. Now I want to store a value with this. So I'm going to make a struct called my struct integer, and that's going to have the header inside of it, and it's got to have an integer in it. And then I'm going to have a different structure, and that structure is going to take a header and then a float, right? So these now are two different types, structs, that both contain a head, and then in the top, and then after that, store a value, right? Now comes the super magical thing. What you can do is, let's say I have a function called setValue, and it takes a pointer to header, right? Then I can actually cast that as an one of these. Now I have to allocate one of these. But what's really nifty about this is that the first thing in this structure is always going to have an offset of 0, right? And that means that a pointer to this structure, this structure, is also a pointer to this structure, because the first thing in this structure is that structure. And the first thing in this structure is this thing. It's the name. And that means that a pointer to this structure is both a pointer to this structure and a pointer to this structure and a pointer to the name. I can just cast them. And that is really, really nifty, because that means I can take this value, give it to this function, and that function can cast it to a header, because it knows that the first value, if it's either this or this, is going to be a header. It can read out a value in the header and say, oh, this is an int. And then it can assign the value and turn this pointer into either the struct int or the struct float. And that means you can basically make, now this is obviously very simple, but you can make something very, very complicated. So for instance, in, I think we had love here. Let's show love. Okay, so I'm gonna see if I can find this. So in love, I have a bunch of things called entities, and they're everything that is being networked. So for instance, here's, you know, blocks, and I think I have, so here's a structure that stores a block in the world, and here is a character. Where do we have the character? Come on, it should, oh, it's not defined there, sorry. Let's do a collider instead. I'm sure I have. So here is a collider. So obviously these structs contain completely different things, because they're entirely, you know, different things, but they're all networked. So they actually all have the same header. So the first entity here is called head. And if we go to that, go to definition, we'll find this thing. And that means that every object in the world has, for instance, a position, a block ID, which block it resides on. It has, you know, previous and the next. This has an ID and all these things. And one of the really nifty things, it has a type. And that means if a function takes, you know, this argument, says this is an entity, I can just say, oh, I know what position it is, I know what block it's on, and so on. But I can also just say, what type is it? And if I know that,
So it's
if I check
totally
that, I say,
unreadable.
oh, it's a character.
It's a fun exercise,
Really good.
but
Actually,
this is
take
kind of
a pointer,
exactly,
and I can cast it to a character.
almost exactly
Now I get access to all the values that are specific to characters.
how
that
objects
aren't
work
blocks
in
or
other
colliders,
programming
all the other
languages.
types of entities that I have.
They
That's a
usually
really
use the
useful
parent
thing.
object
That
as
means
a
I can have
prefix.
some functions that just takes a generic entity, and some functions that take a specific entity, and functions that take multiple different types of entities and can determine themselves what kind of entity they're looking at.
We'll need this
So
to
that
abstract
is
them.
super, super nifty. So let's move forward and see. Another thing you need to know about structures is that computers have something called alignment. And that means that when they store things, they like to store things on on even byte addresses. So here we have a struct, and it has an 8-bit A and a 32-bit B. So this is 1 byte, and this is 4 bytes. So how big is the structure? Well, you would assume it's 5 bytes, 1 plus 4. If you actually do a size of in any reasonable compiler, you will get 8. What the hell is going on? Well, it turns out that the 32-bit value wants to live on an even 4-byte address. And that means that in memory, we're going to store A on the first byte, and then we're going to store nothing for 3 bytes, because B wants to, you know, take up 4 bytes, but it doesn't want to start on, you know, this byte. It wants to start on even 4 bytes, right? So it wants to start on either 0 or 4, right? Or 8, or 12, or 16, or somewhere else, right? And that means in this structure, we're basically going to waste 3 bytes of memory. So what can we do with that? Well, once we understand that, we can, for instance, do this. We can build this new struct, and we have another uint 8, but then we add 3 new ones, right? We add 3 more integers. And since these bytes can live on any byte, basically memory is going to look like this. A, X, Y, Z, and then B, 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 right? So this struct, even though we have 3 more values in it, is actually the same size. We're just using up the memory. And that all depends on us understanding alignment, right? Because if we understand that this 32-bit thing needs to live on an even 32 value, we know that, oh, there's actually going to be some padding here. There's going to be space here. We can actually use that. So when you create a structure, you may want to sort all your stuff so that, for instance, you don't put, like, if you put this one here, now this will actually take up more space, even if, you know, you would think it's the same, but actually the ordering matters. I think I have a slide about that. Yeah.
Ordering matters, but only in some programming languages. A lot of languages are actually free to reorder this stuff however they want. Rust is one. Rust will happily reorder structs to optimize memory usage. C and C++ won't, because they have this, they try to be faithful to what you write. Because the struct was really meant as a kind of utility for almost assembly programmers to define where things are located in memory. So staying faithful to this description was very important in C and C++. Other languages, not so much.
So now you might say, well, if I store the 32-bit first, then, you know, that will be on an even byte, and this one will just be on an even byte too, because, you know, this has to be an even 1 and this has to be an even 4, and since we start at 0, this 0 is an even 4, and this will be on byte 4, and which is an even, you know, divisible by 1. So actually everything will be packed, right, in memory, right? We'll have B, 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 and then A, right? So it's only 5 bytes. Great. No, it's not. Why? Well, because if you do a size of this, you won't get 5, you will get 8 again. Why is that? Well, you still get the padding. Why? Because when you allocate something, you may not allocate one of these. You may allocate a million of them. So if you do that, what's going to come after this? Well, actually, everything again, right? And now all of a sudden, this B, you can't start here, because then it starts on address number 5, which is an even number. It has to start on 8, which is the next even one, right? And therefore, you still end up with this. And if you actually, you know, want to cheat the compiler, you could actually ask the compiler to give me 5 bytes, and this would fit. But if you want to do an array, it will totally not work, and therefore sizeof will not give you 5, it will give you 8. Sizeof always gives you a value that you can repeat, right? That you can multiply with something in order to make an array. And that's kind of something to know. So knowing this about padding makes it possible for you to just by rearranging things in your structs, but just by the order, you can actually do, like, get your memory consumption down. We're going to talk more about why that matters. Yeah, so here's basically some really shifty things you can do where you can manually pack things. So here I basically say I have a uint 8, so I have access to individual bytes, and then I can just, like, go to a byte, and then I can write memory to it, right? That is not a good thing to do, because the reason that your compiler wants to put the data in even spaces is not because, you know, to screw with you. They do that because it's actually faster. On some hardware platforms, if you try to read a 32-bit number that isn't aligned with 32 bits, you may crash your computer. On some machines and some operating system and some types, you may get an exception, and that may create an interrupt, and that may actually be super, super slow, because the operating system might actually have to intervene with your reading and rearrange everything in memory by hand, and that is going to be massively slow. But I still want to show it because it is possible to do, so, you know, do it on your own risk, right? So yeah, here's basically my example of ordering where this is a terrible struct because you have an 8-bit, 32-bit, and 8-bit again, which will give you this: A, bunch of padding, B, X, a bunch of padding. So the type of this is 12, whereas actually you're only using 6 bytes of memory. And if you just take this one and move it here, you're down to 12. So you've saved, a third of your memory just by moving a thing in your struct. So yeah, beware of this basically. Now let's talk about memory blocks. So I just said that memory is just one big array, and you just like have addresses to it, and that is not true at all. It actually is one big array in a way, but it's not actually how the operating system will give it to you, because memory is divided into blocks. Normally it's about 4 kilobytes in each block, and each block has a little flag that says, are you allowed to read here? Are you allowed to write here? Are you allowed to run code here? I talked about that quite a little bit earlier. And each address to one of these do not correspond to where they actually are in physical memory in your machine. There's a little bit of a translation there, and that is because memory is virtualized. So why is this good? Well, it has a couple of really interesting uses. The first is that your operating system can basically tell you that this piece of memory is for this program, and this piece of memory is for that program. And if this application writes in another memory that it didn't.
So the video is talking about
I can crash that application.
very different things. Like, no, it's not C related at all.
Another application. In modern operating systems, there's ways for applications to tell the operating system that actually I will allow this other application to read my memory, but that is a very, very special case. Normally, you do not want that. Normally, you want each application to run its own memory and not be able to mess with any other application's memory. So this creates some interesting things, because since these are virtualized and you don't actually get access to them, you can rearrange them. And that is the first clue that realloc is an awesome function. Realloc basically allows you to take a piece of memory and then reallocate the size of that to either make it larger or smaller, and whatever is in that memory will still be there. And that means you can do some really nifty things. Now, obviously, let's imagine you have a big array of memory and you want to have, more memory. Maybe the memory right after the memory you asked for is taken by something else. So what realloc needs to do then is basically copy all the memory into another place where there is enough memory, right? It needs a new place where it can find contiguous memory that is that long. And copying this memory might potentially be really slow. That is why in most literature you read, realloc is seen as a bad function because it may require copying of memory. Now, I actually think that's wrong, because since it's actually sent in blocks like this.
Nobody says realloc is wrong. Realloc is actually the optimization of alloc for growing memory. It's strictly better than deleting and allocating new memory.
And since those blocks can be reassigned in the hardware, you'd never actually have to move more than one block. And if you think about it, if you allocate, a gigabyte of memory, that is going to come out as a contiguous piece of memory. Well, what if you have a gigabyte?
If I remember correctly, realloc will fail if it cannot allocate. Yeah, it will always succeed.
free, except it's not contiguous. Can you not allocate that memory? Yes, you can, because the memory manager, which is a little piece of hardware, can actually build a table of memory and say, okay, you want a gigabyte of memory, we'll take some from here, we'll take some from here, we'll take some from here. And whenever you ask for these addresses, I know you're actually meaning these little pieces that are, you know, scattered out in the actual hardware, and I can give you that piece of memory as if it is one big contiguous piece of memory. And that means that when you realloc, you actually don't have to move every piece. You can just like fix the end piece and then just find some random pieces, you know, that you can sort of tack on the end, and they don't actually have to be right after. If you're a Windows user, and I'm sure there's something like this on Linux, because, you know, Linux is awesome when it comes to things like this, there is a little program you can download called gflags. And gflags allows you to set some really nifty rules for how memory is allocated. So if you allocate 1 byte of memory, the processor will not give you 1 byte. It will actually have to assign to you an entire block. So it will actually have to allocate 4K of memory. But then if you say, oh, I want, you know, 10 bytes more, you won't actually get a new block. It will say, well, you only asked for 1 byte and I gave you 4K. So I'll just give you, you know, a pointer to the same block, but right after that byte. Because, you know, not actually right after, but in the same block. And that means that you can actually read and write from this thing. Now, what that means, if you, let's see if I have a slide for this. No, I don't. I'll write one. Okay, so let's say we have our memory, and the memory is like this. And then you have our first allocation is here, and then our second allocation is this, right? It's get given there, and then we have the third allocation, and maybe there's a fourth allocation, right? And then I say like, oh, I want like a massive new allocation, number 5, which is this big. And then it may say, okay, we need a new block. So I'm going to do that, and I'm going to put number 5 in this block. It doesn't have to be this, but
we don't need this
an example.
anymore.
Now, the problem is that if you are in allocation 1, which is only 1 byte large, and you happen to say, let's call that allocation A1, and you do this, it's equal to 0, then you're actually writing over something in allocation 2, because it's in the same memory, you own it, and the application cannot crash because it's totally legally your memory that you're allowed to do things in, except, you know, it's not the way you think it is. You think you're writing to allocation 1, but you're really writing to allocation 2. So you fucked up memory. And this bug will frickin' kill you. Like, this is the worst bug you can imagine. Let me actually show you the same bug, but on the stack, right? So now I'm gonna write this is a nasty bug. So I'm gonna write uint a, which is my array, and I'm going to put 10 values here, and then I'm going to put I here, right? And now I want to actually fill this array.
It happens for me as well.
Right?
This is...
Sounds easy, so I'm going to do for I is equal to 0.
I fully agree. This is like one of the worst things that can happen.
And now I'm going to introduce a bug. I'm going to write
It's incredibly hard to debug because the program
right?
usually just keeps running until it uses this memory,
0.
if it happens to need it for
Now,
something.
what's going to happen with this? Well, most likely, depending on compiler, but what is
There's maybe just one more worse
that
type of bug, but
compiler will put A as an array in memory and then put I right after it. And that means that when you write outside of A, you're going to overwrite I.
yeah,
So
bounce
what's going to
checks,
happen here is you're going to get,
they are often worth the price.
because I is going to get to 10, and then this pointer now points to I, so this actually overwrites I in memory. So now I is back to 0. And then you start over. So this will create an infinite loop, which is completely super weird. And when you look at this code, you don't see an infinite loop. You say, well, I goes to 11 and then it stops. And I never change I anywhere except here. This is the only thing. I can only go up. Why does I get set into 0? That's freaking crazy, right? And this is a really, really hard bug to find, right? Therefore, I am really scared every time I put an array on the stack, because this is basically like, this sets you up to fail, right? I'm not saying you shouldn't ever do it. Just be aware that this bug can happen, right? So why do I talk about this? Well, because gflags is a lovely, lovely tool. And in that tool, you can tell Windows that every time I do an allocation, give me an entirely new block. So what it will do, instead of doing this, it will do this. So when I ask for 1, it won't give me that byte. It will give me this byte. That is the last byte in the function. And then after this, it won't give me this thing. It will actually create an entire block here that I'm not allowed to read or write to. It will create a kill block that's just like, if you touch me, you die, right? So now, and then it will create a new block for number 2 that will end here. Let's keep doing this, and then another kill block. Let's like keep doing this. Right, so now you all of a sudden, you'll say, wait a minute, this is eating a lot of memory. All of a sudden, it's like, I keep typing here, and it's like, this should not even be here. It should be here. So it just keeps going, right? So I'm just using a shit ton of memory here. But what's really good is if I overwrite this, if I write this code, when gflags is turned on, I will crash. And that means that my program, it will be very easy to debug my program. The thing you will notice that once you turn on this flag in this gflags application, your whole operating system will become quite unstable. Everything will crash. You will find out how buggy and terrible all the software you run is. Your browser will crash all the time. Everything will be quite terrible. So you usually don't want to actually have gflags turned on unless you have a very dedicated machine that only you develop on. But it really makes sense turning it on like every few weeks. Just turn it on for, and run your application and see if it crashes, because if it does, you'll find all these bugs. So we get back to the theme that actually having your software crash is really good, because it allows you to find the bugs rather than just like trying to hide them. Okay, moving on. The other thing you need to know is that memory is really, really, really slow. If you read 1 byte, if you have memory in a register, it takes 0 bytes to read it, because it's basically in the processor. If it's in the level 1 cache, which is a very small piece of memory, that is the fastest piece of memory outside of the register, it will take between 2 and 3 cycles to read or write something from that memory. Now that memory is ridiculously small. Now there's a larger cache, which is the level 2 cache, and that may take between 10 and 15 cycles to read. If you have main memory, which sits on your motherboard, which is really, really far away from the actual CPU, it may take as much as 50 cycles to get a single byte from that memory. Now, if you have a modern, SIMD processor, that processor may be able to do 4 multiplications for every cycle. And that means that reading a piece of memory can take 50 cycles. And in that time, you could have done 50 times 4 multiplications. That's 200 multiplications. And that's why this code, doing all these multiplications, may, at least in theory, be faster than doing this, which basically is just like, get me a single byte of memory. This is something that a lot of people don't understand. Memory is ridiculously slow, whereas math is ridiculously fast. And therefore, when you optimize your code, pretty much the only thing you need to know about is this memory? Am I accessing a lot of memory? Can I reduce the amount of memory?
Yeah.
And can I get the memory to be in the cache? So how do I know if it's in the cache? Well, you can query that if you're really anal, but the basic idea is that whenever you read a piece of memory, the CPU will say, hey, you want
Why
this
doesn't
piece of
this
memory.
work?
You probably want
You'll ignore
memory that
this.
is really close to that memory. You're probably doing something in this area. So I'm not going to read 1 byte. I'm going to read you a bunch of memory around that memory. And a smaller piece of that I'm going to put in the level 0 cache, which is the fastest, the level 1 cache, which is the fastest piece of memory. And a little bit more of it I'm going to put in the level 2 cache, which is larger, but therefore slower. This is a fundamental problem of caches, is if you make them really big, it takes a long time to find the memory in them. Like the search algorithm gets slower. Whereas if you make them small, they're fast. So therefore people make multiple caches that have different sizes, and the larger they are, the slower they are, but the more stuff you get, the less you're likely to have what's called a cache miss, where you ask for something and it's not in the cache and you have to go get it in the slow memory. So that's why you have multiple levels of caches. There are machines that have 1 level of cache, there's machines that have 2 levels of cache, there's even machines with 3 levels of cache, and sometimes even 4 levels of cache. So let's have a look at how we can do this. Let's start with linked list. A lot of people say, use linked lists everywhere. Linked lists is how we teach people to write algorithms. And I think that's a really bad thing. But
There are no people who will say use linked lists everywhere. This presentation is really nice, but the one thing I dislike about this is the constant strawmanning. Constantly saying something stupid and then explaining that it's stupid. Nobody says this. Nobody says use linked lists all the time. In fact, people say avoid linked lists as much as possible, and that's not always the case. Like sometimes linked lists are useful. A more common statement is that it's more likely that people will say never use linked lists than always use linked lists. And both of those statements are obviously wrong. There are use cases where linked lists are great.
linked lists are about the worst thing you can do for memory coherence, because every link in a list resides in a different piece of memory, and you keep reading all over the memory just to get to where you're going. You jump around in memory, and that means you're probably going to put it in different places, and you're going to not.
It's not necessarily the case. So there is a fun way to use linked list. If you have something like that, where you have value in a node and a pointer to next node, you actually can put a linked list in an array. So something like that. And then when you allocate nodes for this linked list from this array, you can have a counter. Buffer end, right? If you allocate nodes from this array, the nodes of the linked list are going to be one after the other. They are going to be super compact. So this way you can push them closer together. You can even actually split this, and instead of having a struct like this, you can have so in this form, this is a linked list. I know it doesn't look like a linked list, but it is. An index specifies a node, and you can read the value of the node by accessing the values array, and you can find the index of the next node by reading the next array, and even make this smaller, like 16t in this case, because the space of all values is probably rather small. And now this will fit in a single page of memory. So no round trips to the main memory even.
Not have it adjacent in memory, and therefore you're going to get cache misses. So a normal linked list like this, like where you have a list of something and you go to the next and for loop, this is terrible. Now, if you have an array, on the other hand, you've actually placed them next to each other.
And I wouldn't use adjectives such as terrible. There are often situations where silly code is just fine. not everything has to be, you know, incredibly optimized. Sometimes you care about speed, I mean, writing the code, not necessarily computer executing it.
They're in memory. That means it's going to be way, way faster, because when you load in one, you're most likely loading in the next one at the same time. This is way, way better than this, right? So that's why realloc is really good. We talked about realloc, and I said realloc is not actually as bad as you think. Well, now I'm going to talk about why it's awesome. Have a look at this code. This is our array length. And what I do if I want to add something is I say, hey, is this length of array, the amount I use of this array, the same as I have allocated? And if it is, I'm going to allocate 16 more values, and then I'm going to reallocate this thing. That means that every time I add this, I won't actually run this. Every 16th time I add something, I will actually need to realloc, which means that realloc becomes a fairly rare occurrence. Now, obviously, if I change this to something really big, like 2000, 1024, and now it's going to be super rare, right? I'm going to spill a bunch of memory, because if this array is only 1 big, I allocate 1024 times as much memory as I need, which is obviously a waste, but it might not be so bad, right? I can also have it totally different, where I basically say double the size of memory every time I run out of memory. Now that will, scale exponentially, obviously, so I might, lose more memory, but this is going to make it even rarer that I have to allocate memory, especially if the array, sort of grows and shrinks. Then very rarely will actually sort of top out and actually get larger. And this code will probably only run realloc a couple of times. It will never get smaller, but it will actually sort of very rarely require you to do realloc. So the fact that you're doing realloc very rarely means that since you now have a piece of memory that is this huge, piece of memory that is all linked to each other, and they're all sort of adjacent to each other in memory, it means that actually operating on this piece of memory is very fast. Now remember, here when we have a linked list, we have to store the next, right? So this is actually allocating twice as much memory, because I'm storing 2 pointers instead of actually just storing the pointer. So I'm wasting memory here as well. In fact, here I'm always using twice as much memory, which is the same thing I'm doing here. So when you look at this, you might say, wow, you're just like guessing you need twice as much memory. That's a vast, over allocation. Well, actually, it's never worse than this. This is always worse, and this is how they teach you to do it in computer science. That's why I keep saying realloc is awesome. And if you want to remove something, you just do this, right? You take the last element and you put it in whatever you want to remove, and you do, array minus minus, and now you're gone, right? So this is also super fast, right? And you might say, well, yeah, that's easy, but what if I actually want to keep them in the same order? I want to remove something, but I want to keep them in order. Now I have to move everything. Whereas if a linked list, I just remove a link in the middle, especially if I have a linked list where
maybe I could keep this value in the
next,
widget.
then I can really easily, do a little jank in the middle, and, I don't have to go through the entire array. That's much faster. Yes, that's true, but usually when you want to move or remove something, you first have to find it, which means you have to walk through the memory anyways. And that means that a backwards remove is faster than linked list. So here is my backwards remove. So what you do is you start at the end of the array and you walk backwards, and you say, every time I come to a piece of memory, I check, is this the one I want to remove? And if I am, I'm done. And then I basically just save the one I'm at and overwrite it with the previous one, and then keep going. So since I'm already touching the memory to see if it's the one in I want to remove, I am actually in the cache already, and I can overwrite the memory. This is actually quite buggy. But this type of code is actually faster, and it doesn't matter if you go backwards here instead of going forward, which you probably do with the normal linked list, but it doesn't make it faster or slower which way you go. So this is actually a much better approach. I actually very rarely use this. Usually this will suffice. It depends if the array has to be sorted or not. So okay, so let's see what's next. Let's talk about what I don't like more. So this is a mistake that I see a lot of people do. They store data twice. And sometimes you have to, but if you can avoid it,
Yeah.
it's a really good thing.
It's a source
So
of
here is
tons
my
of
function that I
errors.
want to store, and I store the width,
Redundancy in
the
data.
plane, and then store the area. of the plane.
Redundancy
Now,
is good
obviously,
in
you
program
have
source
the width
code,
and the length.
not in the
Compute
program
the area.
data.
Now, this to me is a bug waiting to happen, because if I have this, somebody might change width or length without updating area, right? That could happen, and therefore I don't actually know what the canonical, definition is, right? If I every time I need array, actually use width and length and multiply them together, that's actually much safer. Whereas if I store this, this may or may not be consistent, whereas this is always consistent. This cannot be buggy, this can, right? And some people think, well, actually, it's better to store area here because then I don't have to compute it. But yes, we just learned that actually memory is what's, accessing memory is what's expensive. Math is basically free. So therefore, it's actually better to have a smaller piece of memory, and that will, make everything more packed together, and that's more valuable in terms of performance than saving that multiplication. Now, this is a ridiculous example, of course. We could imagine having something where computing area would be massively slow, so that actually I need to store that because it's too slow to compute area every time I need it. I need to cache that. So obviously that's something you need to do. I work a lot in computer graphics. Computer graphics is a lot about caching and making structures that are optimal for reading in a certain way. Maybe you have an octree or something like that. If you do that, I would always do this, which basically is create a void pointer where you hide this internal structure, and then you have a function called width set or a width get, a length set, and a length get, and an area get. And here you have parameters, and then I can guarantee that since you cannot touch the internal value of width except calling this function, this is your only way of changing width, and therefore I can guarantee that every time you change width, area gets updated appropriately. This is like hard-coded to never bug. And I always do this if I have to do this. But just knowing this, it's like, as a rule, try to avoid storing any data twice. That is a just like really good thing. Okay. So now we're going to talk about some smart things you can do with allocations that are a little bit more complicated. So here I'm going to store an array, and I want to store the length of the array. So the normal way of doing that is to do this, right? You basically say, I want to allocate this structure. So you allocate that structure, and then you want to allocate a certain amount of bytes. So you do an allocation and set that in the length, and then you actually allocate the array, and then you fill them out. Now, the problem here is that we're actually doing two allocations, right? And that means that these two pieces of memory, the one that stores this, which is kind of the container of data, is in one piece of memory, and then the actual data is in another piece of memory. So we have two pieces of memory that may not be adjacent to each other in memory, and therefore, in theory, could be slow, right? A smarter way of doing it is doing this. I build a struct, and in that struct, I have length, and then I have data, and I make an array with just 1 point of data. And then I allocate this by doing size of this thing, and then I add to that the number of bytes I want to store. And then I do minus the times length, the length of the array, minus 1, because I already have 1 here. And then by doing that, I can now get just one allocation. So basically, I say that even if I only define this as 1 byte, I can just like write this out as multiple bytes, because I know what the hell I'm doing. I know I'm over allocated. Now in C99, they've actually added this to their language. So in C99, you can do this, which basically says, I want a struct that is type length, and then after that comes ints, but I don't know how many. So it's 0.1. And if you use this, you don't actually have to do the -1 here, because size of array will only be size of length. And if you use this, byte has to obviously be at the end, because if you have, for instance, you know, float x here, let's put this back. If I now write over this, I'm going to start writing into x. So I'm going to overwrite x. So therefore, if x needs to live here, x needs to live here, and this needs to live at the end, because I'm basically writing outside of memory, right? So this is actually totally legal, and this is actually faster than this, because you're now doing only one allocation. And actually the allocation in itself might be slow, but actually accessing into data will also be fast, because if you access length, you will read this into memory, and that means you will probably read the beginning of this array, whatever comes after length, into memory too. And if that's the memory you want to read, well, that's a good thing. So this is actually faster. Now we can do some even trickier things. So now I'm going to do two structs here. One struct A and one struct B, and they have like random things in them. I can allocate those as, you know, 2 allocations, but I can actually also allocate them as 1 allocation. So here I do a malloc, and I do size of struct A, and then the size of struct B. So now I have basically a piece of memory that is big enough to fit both of them. And let's say I have struct A, that's a pointer, that's what I allocate to, so I store that first in memory. Now, if I go 1 array unit forward with that, I'm basically going to end up at the address where struct A would have its neighbor. Now, I can do that and then take the address of that and cast that to struct B. Now all of a sudden I have an access point to B. So A and B are now 2 different structs, but they live adjacent to each other in memory, which might be useful for performance. Now this is scary. This is dangerous. You're supposed to be, you know, worried when you do this, because these 2 structs may have different alignments. So if this, for instance, isn't this, let's say it's just a uint 8, something like this. The alignment of this, you know, if I go, this alignment of the structure,
I don't think this will cause any issues. It was mostly about performance.
And therefore, when I do
alignment.
this, I'm going to jump 1 byte forward.
Was.
And that's not going to be aligned by this, because this
It's not
even 4,
necessarily still the case.
Even 8, because it's a size 8. So this will actually maybe not work on some machine. It may fuck up your thing. So when you do this, you really have to be on top of your alignment. You should really, like, this is dangerous stuff, but if you know what you're doing, you can actually squeak out more performance. And also, I think just knowing how this works is just like it's good practice. Using it is maybe not so good practice, but if you can do this, that means you really understand how memory works, and that means you're probably a decent coder. So let's talk about some other tricks and trips. And
You want to
I really
remove this
like
timeline argument?
stride. So stride is a thing that C programmers sometimes use to annotate, sort of tell how big a piece of memory is. So let's say we have a function that takes a bunch of RGB values, pixels, and they're 8-bit, and does something to them, right? So this is my color corrector, for instance. Now, normally you would think, I'm going to give it this. This is all my things. Now, this requires these RGB values to be next to each other, right? So you do RGB, 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 RGB forever. Well, what if I don't store them like that? What if I have something else? What if I store a buffer with RGB A? So I have an alpha value there. Then I can't use this function because this only takes RGB. So what do I need to do? Well, I need to make an RGB buffer. I need to copy all my RGB values to that buffer and then give it to the color correction function and then copy them back to my RGB alpha buffer. That's really slow. So a smarter function is like this one. It says, I want RGB, I want how many, but then tell me how long this structure is. Tell me how many values I should jump. So when I call this for RGBA, I can say, here's my RGBA buffer. I have a pixel count of how many pixels I have, and the size of every color value is you went 8, but it's 4 values, and that means for every pixel you want to do, don't jump 3 values, jump 4 values. Skip whatever comes after. Now that's really nifty because now I can even give it a struct. Let's say I have a struct here with a bunch of values. I can say, oh, I got 10 of these values and they got colors and there are 3 values in them. I can basically say, oh, give me the first structure and the value color. So I give a pointer to this value. And then I say, do 10 of them, but actually do the size of this entire struct, right? And now it will actually it will ignore this and it will ignore that, but it will fill in all the color and that means that this function that has the stride value is much, much more versatile than this function. That's why I think that actually using stride is really, really good. So please use stride. So talking about a little bit more about like high level, like how you construct your code. I think that what's really important and what people don't teach in computer science is architecting. And architecting is really about thinking about how you structure.
Yes, in computer science they don't teach software architecture, of course.
Your code and your approach to building an application. And what I think is the most important thing is to find your primitive. So let's say you make a rendering engine. It's really easy to say, well, I want to support everything. I want to have splines, I want to have NURBs, I want to have polygons, I want to have all the different kinds of things, right? The problem is that once you start implementing this, you're going to realize very quickly that you get a lot of work, right? Because let's say you want to do a reflection thing. Now, all of a sudden, you need to compute that for a sphere, for a polygon, for a NURB, and for a spline. You have to implement that function 4 times. Now instead, if you say, well, my rendering engine only does triangles, now then it becomes very simple to do that, right? You just implement it once, and then you say, well, if you want to do NURBs or something like that, you first have to, convert them into triangles. And all I do is triangles. Now, if you pick triangles, you're going to have a bunch of limitations because triangles can't do certain things. If you pick another one, like subdivision surfaces, which, Kaplan-Clark subdivision surfaces, you can do way more, but they're also more complicated in other ways. So you have to basically pick your primitives, and the smaller your primitive is, the easier it's going to be to write. So if you write, say, a compiler, a language compiler, the smaller the language, ergo your primitive, the easier it's going to be to write really cool features in your compiler. If the compiler has 1 million features, if the language has 1 million features, it becomes really hard to write a debugger that cares about all those things, that does smart things with all those things. And that goes for everything. Say you want to write a text editor, find out how you can store your text in a really smart way so that you can access it really versatilely. If you have a bunch of different ways of storing text, that means a bunch of your functionality has to be able to operate on all those different types of text, and then all of a sudden your code becomes really big, and that makes it really hard to develop. So this gets me to another thing, which is I think, when I think about code, I think you should build a mountain. And what I mean by that is you should not be afraid of writing code. There's something about how people talk about code where they basically say don't implement anything. And they keep telling you that, oh, everything is hard. Like, don't do this, that's hard. Don't write your own compiler, that's really hard. Don't write your drivers, it's hard. Don't write an operating system, it's hard. Don't write anything because it's hard. Well, if you're going to be a good programmer, that's what you should be doing. You should, as soon as somebody says, oh, this is too hard for you, then you should be like, wow, I have an opportunity to learn something. This is something I don't know how to do, and therefore I should be doing it. That is what I think you should do. You should not be afraid of writing code. If you are afraid of writing code, don't be a programmer. There's lots of other cool things you can do.
Yeah, it really depends. I agree with Eskil here, with a small print that if you want to achieve some end goal, like if you want to make a game, then probably rewriting everything from scratch is a bad idea, because you will just spend eternity working on your game engine and not the game. for learning, yeah, it's the best way to do learning, essentially.
Life, if you want to do code, right? You learn by implementing things, not by coding. And when you implement something yourself, you will actually have something that won't age. Now, if you use someone else's code, they may stop developing it. They may, require some code or some compiler or some operating system or something that you don't have access to. And when that disappears, you're screwed. Whereas if you wrote the code, you can fix it. You can change it, you can update it, and you can make sure it always runs. And if something is wrong with it, guess what? You have an expert who can fix it. You are the expert because you wrote it. And that turns out to be super, super valuable in the long run. And that's actually why I have a bunch of names of products here, because I think that, when people talk about Apple and all the things that Apple have done that have been very successful, something that isn't being brought up is that they built a frickin' mountain, right? They implemented QuickTime, which was this thing to do images and sounds and things like that. Once they implemented QuickTime, which wasn't that interesting, it was a technical thing, nobody cared about it, that allowed them to write iTunes, right? All of a sudden, people gave a shit about iTunes. Wow, I can, they could do an iPod now. They can do all kinds of cool shit, right? iPods are really cool. And then they said, well, what if we write this thing called WebObjects? So what's WebObject? Well, it's this super nerdy thing that allows you to build, web platform things. Okay, nobody cared about that. But all of a sudden, they say, hey, we got iTunes. We got this, music player. And we have this web thing. So now all of a sudden, we can make a store. We can make a store where people can buy music. Awesome, right? So now everybody cares. But then at the same time, they did OS X. They updated their, their operating system because the previous one was, frankly terrible. And they added OpenGL and things like that. And all of a sudden, they could do something like iOS. And all of a sudden, once you have iOS, which is, the operating system they have iTunes, they have a store. Holy shit, they can make an app store. Holy shit, now they can sell stuff. Oh, and then they say, oh, we should make a browser. And everybody's like, why are you making a browser? There's lots of browsers already. Well, they made Safari. And all of a sudden, now they can make an iPhone. They can only make an iPhone because they built all these pieces, right? And that's what I'm saying is like, whenever you build a piece of technology, don't think of that technology as the endpoint. Think of that as a part of your mountain. When you build an application, you should build a very small house, right? Build a small house on a big mountain. The applications you build should be small. The technology you build should be huge, right? Every time you build something, if you build a music player, don't build, spend your time building the interface thing, and think that's, build everything as one big thing. Build an interface library and then build a, sound library. Once you have that, building the actual, application that plays music should be trivial. But then you can build a totally new application that plays sounds. You can make a totally new application that has an interface, and because you've already done it, right? And that's what I think is really important. Build a mountain. So let's move on. Another thing is I think you should fix your code right now. If you don't like your code, fix it now. A lot of people tend to think, I'll fix it later. I don't have time. And that just snowballs. So I don't ever try to wait. I have almost no technical debt in any of my code. Because if I don't like my code, I will rewrite it. And I will rewrite it right now. It's never ever going to be as easy to rewrite your code.
It is very hard to do this. It's possible to write write programs like that. It's very, very time consuming. Even the simplest thing takes a lot of time because the architecture keeps changing. I hope that with AI agents, it will become more possible.
Code as it is today, because the more you use code, the harder it is to change it, and therefore you do not want to change code. And that's why change it today, fix it now, don't fix it later. Another thing is that if you work at a company or, if somebody hires you to do something, if you hack something together, you're basically going to teach your boss that you can do things quickly. And that hack is, they're going to say, why did it take you 1 day to make a prototype that does 99% of what I want, and then it takes you 6 months to add that 1%. They're going to fire you because you're lazy. Well, you weren't lazy at that. You just fucked up by giving them too much in the beginning.
No, nobody's going to fire you. I've seen... sorry, I haven't seen... I've heard of people being fired, and it's not because of implementing stuff well. It's actually quite the opposite.
You should give them very little. You should give them only what's completed. Only show your manager what actually is debugged and finished and ready. That's what you should show your developer, your manager. Then they will have a realistic idea of how long it takes to develop things. If you cheat, if you try to show off by, hacking something together, it will just bite you in the ass. Don't do that. Be realistic. Write everything as you want it to. As you want it to be for real. Don't spend forever, but write it right from the beginning. That to me is like a really, really important thing, and it will just always pay off. So now I'm gonna be going up a level. So I've been talking about deep stuff, but now I want to show you how to actually write real applications. So I've showed you a bunch of C stuff, but let's talk about how to actually do UIs and applications and cool shit. So I want to show you how my UI library works. And my UI library is a bit specific. Sorry. I'm getting a call I can't take right now. So I'm going to show you, this is my widget. Now, a widget in my UI toolkit can either draw or have an event, basically if you have a button and you click on it, or it can update itself. And all of those things happens in a structure I called input. So all my input for my widgets, for my UI toolkits are stored in this. Now, why is this really useful?
Now,
well, it means I can have a...
This is an interesting architecture. It's like multiplexing many function calls in a single function by putting those modes.
Function that is a button that I can call multiple times, but for entirely different reasons. So even if it's one function, I can use it in different sections. Let's explore how that works. This is how most UI systems work, right? You have an initialization phase where you say, I want to create an element in my UI. It's gonna, right? So you create an element, you get a handle, and then you say, in this element, I want a button. I want it to be called hello. It was gonna be on X and Y. And then I want to have whenever somebody pushes the button, I want this function to call, and then I have a function, and then I have a user pointer to that function so that I can pass in data, blah, blah, blah. And then I have my main loop, and in my main loop, I say, run this element, right? So what's nice about this is that this element can now run either to, click or to draw this button. This to me is very annoying. This is how people do it in a sort of object-oriented fashion. So now I'm going to show how I do it. I do it like this. I'm first going to show why you shouldn't do it like this. Let's say I now want to have a button that moves, right? So now I do the same thing over again, but now I have to actually...
So the way that Haskell is recommending to write UI is not something I would advise somebody else to do. It's a fun and interesting way to write a UI library. It would be very surprising to people if they saw something like that. It could actually be very confusing, and when working in a team, it's usually better to have code that people around you will understand than clever code that only you understand.
Move the button, right? In order to move the button, I need to have a way to talk to this button. So I need some kind of ID for my button, and then I have a function that says, oh, in element so-and-so, in this ID, move this thing around here, run my element, right? So now there's a lot of IDs and things that we're keeping around here that just makes this very nasty, right? So wouldn't it be much nicer if it looked like this, right? I just want a function that says draw a button, and it takes an X and a Y, and I can put whatever sine function if I want to move it. and then, you know, say the name, and then it returns true if somebody presses it,
Is
right?
it going to...
That would be awesome. That would be much, much easier.
So there is a trick that many immediate mode user interface libraries do, which is smuggling the state. So you quite often need to maintain some kind of state throughout in the UI to draw it properly, to draw it efficiently. You can draw it without any state, but it's going to be very inefficient. You're doing everything from scratch, every frame. So what happens is the state can be encoded in a global variable, and it can be hidden from the user of the library, so that the user isn't aware that there is some state, but the state is just kept behind the scenes.
Here, right? The problem is, what if I want to do some more stuff? Let's say I want to draw a button and I want to draw a surface, right? When I evaluate this function, I don't know if I'm going to draw a surface afterwards, which means this surface might cover my button, right? And that means I can't do this test. I can't reply to the question, is somebody clicking on the button? Because I don't know yet if there's going to be a surface covering it. Well, you may say, well, I want to just like tell the application that there's a surface first. Well, obviously that's great, but now I can't draw the button because I shouldn't draw the button because the button needs to be drawn first so that I can draw the surface on top of it. So what the hell do I do? Which order do I do these things in? Right? I can't do it. It's an unsolvable problem, right? So even though this looks really nice, it can't actually be done. So let's have a look at how I do it. Let's add an ID, right? If I somehow knew which button this was, and
I expected a stack. So this is surprising.
Internally, I could do something really smart. What could I do? I could actually store where this button is, and I could store where this surface is, hiddenly from the user, and then I could resolve all the clicking. And that means that if I run this loop in order to draw, I just draw this, and then I draw the surface on top of it, and I register that when I drew this button, it got overwritten by this thing, and I now have a little memory somewhere in here that says that ID1 no longer exists. ID1 has been overwritten. And then when I come again and I say is somebody clicking on this ID, and I can check where it is and do a click test, and I say yes, I should be clicking. Oh wait, no, because when I drew this thing, this got overwritten, right? And now I don't have to store state. The state can be stored inside the button. So this whole UI toolkit can now internally deal with this. And that means that my UI tool becomes super easy. I don't have to keep around many IDs. Well, I just said I needed IDs, right? So don't I have to allocate these IDs somehow? Like, don't I have to have like create ID function? No, I do not, because I can use anything. The thing is, as long as I give it a pointer, it can be a pointer to anything. So as long as I give it the same pointer, I can do anything. So for instance, if I have a slider, I usually have a pointer that the slider, a value that the slider is changing. I'll just give it to the pointer to the slider, right? So almost all the time, you happen to have a pointer around that is unique. As long as it's a unique pointer, the slider knows that, oh, I'm the same slider as I was last time. Therefore, ergo, I can, resolve who I am, and I can do all the nice, storage thing without actually having the user have to allocate something. If I absolutely positively need a unique ID, I can use malloc, or I can just use a string. I can do this. I can say, like, demo. And obviously, since this will be allocated somewhere, it will be somewhere and have a pointer, and that pointer will be unique. Done. Right? Super easy. So you can really, by using these kinds of pointers, by using pointers not as a pointer to data, but using as a unique ID, you can all do a really cool stuff. Some other things. I'm wrapping up now. This is a piece of code that everyone who does anything with computer graphics should have. This is Carmack's inverse square root. I've reversed it again. But this magical code that no one quite understands how it works unless you're a crazy mathematician, actually does a very good square root approximation. And only it's a million times faster than the square root you get in standard library. What it actually does is like it takes a float and casts it to an integer and then uses like this number minus whatever and casts it back to a float. And for some freaking reason that no one quite understands, this turns into a square root. So I didn't know about this for a long time, and then when I actually found out about it and started using it, it was like a door opened to a new universe. So definitely look this one up. I'll be posting these slides, so
It's
you'll be able
a
to
little bit
find it.
faster square root. It has slightly
This is
higher
another
error.
one that I use. I went to SIGGRAPH a bunch of years ago, and this is the magical random number generator that just give it a seed and it gives you a random number. And this is very few instructions.
There are better random numbers generators now. There is XOR shift. XOR shift is the new king.
For, you know, things like stochastic ray tracing or things like that. I use it all the time. I do procedural rendering and things like that. So it's my best friend. And that's pretty much it. That's it for my talk. Obviously, you can email me. That's, you know, email me questions. I'll you know, I do work for other people. You can also follow me on Twitter. If you found this talk, you may already have found me on Twitter, but I post usually when I stream and things like that. You also have my website, Kelsolar, where you can find my games and stuff like that. I'm going to update it sometime. Then I have Unravel, which is my next big project that I'm going to be doing. And I also have gamepipeline.org, where you can download all the source code for everything you saw today, almost. You can download love source code, but all my libraries, I have some really, really nifty libraries that I'm sure you're going to like. They're all open source under FreeBSD, so use them as much as you like. And if you have bug reports, please send them to me. And I think that's it for me. So thanks everybody for watching.
Oh, that was a nice video. I guess I will do a break here, and in a moment we will watch the new presentation by Eskil.
3D graphic.
This one. Yeah. The one about C wasn't really about C. It was more like an introduction for new programmers. Some of the information there, very little, went out of date. Otherwise, it's a decent presentation. One thing I would improve there was there is this orthodox approach to programming, which is probably wrong. Programming is type of engineering, so it's about picking the best tool for the job without staying dogmatic about any techniques. Strong convictions can only make you a worse engineer. It's not art, right? If you're an artist, you can have this kind of mindset, but not when you're a programmer. Okay, so break. Okay, so let's watch it.
That could synchronize multiple applications sharing 3D data called Verse, which is a little bit like Omniverse, actually. I've written my own 3D modeling tool called LuckRO, which is a subdivision surface modeler. I wrote a game called Love for a long time, which was a procedural first-person action adventure game, that network game, and it was scratch written. I've written a fully automatic UV unwrapper called the Ministerial Flat, which is an algorithm that basically does UV unwrapping, but very, very much like a human would do it. This is also licensed in Cinema 4D. So if you have a license to Cinema 4D, you can play with it. If you don't, you can go to ministerialflat.com and download a copy. I've written the file format Haxa, which is a really simple asset format for loading polygons and pixels, basically. Mostly for like people who are like us who want to program and don't want to have a complicated thing and just get some pixels into our little toy engine or real engine. I worked a lot with LED controls, so I've written several applications to do where you can design LED setups. And yes, I represent Sweden in the ISO VG14C standard. My main things that I'm interested there is undefined behavior. I'm authoring a paper that is going to describe once and for all how UV works. I'm interested in the memory model and concurrency. And I'm also working on a hardware project called Eskil, which is going to be a luxury brand for some cool hardware that I can't really talk about yet. And last week, I launched a gaming studio in my apartment. And so that's really cool. 2 employees. We're going to have a lot of fun. And everything is going to be streamed. So you can find me most days on Kelsolar. And I stream pretty much all my development. So come and ask questions, come and hang out. So I want to talk about a problem I have. I have trouble finishing software. And I have trouble finishing a lot of things because I like starting things more than finishing things.
So by looking at his history,
It's hard to...
it doesn't look like he has this problem. So much. So many programs. Big programs as well.
To finish things. I think most people who've ever tried know that. But I want to talk about in a larger sense, because I think we have a culture of not finishing things in software. And I would argue that good quality software is finished. And I want to talk about the word quality for a second, because when people in the software world talk about quality, they tend to use maintainable as like this thing we should have in software. And I don't think that makes very much sense in any other context. Like if you bought went to a car dealership and they said like, oh, this is a super high quality car. And you'd be like, oh, great. So it's not going to break. Oh, no, it'll break every day, but it'll be super easy to fix.
But this is an aspect when buying a car, how easy it is to fix it.
You wouldn't think that was like a high quality car, right? This is very weird. Why are we like this, right? Well, some people say, software can always be improved and, it's a continuous project and, Well, imagine if this was like that for building a bridge, where we started building a bridge and it was like, when can we go over the bridge? And people are like, well, it's not the greatest bridge that could ever possibly be built. And it's like, oh, they built something in China that was really cool, so we need to restart everything. And it's like, can we get to the other side at some point? At some point, it's actually more valuable to have something that works and that is finished and completed than having something that is continuously being improved. And is it really being improved? Can I trust you to make it better? I mean, we have a lot of examples of like, keep working at it a long, long time and it's not getting better, right? I think we have this, expression now, and shitifications, that's like, if we just work on it enough, it turns into shit. And I think people need a goal. Like, I think that's an important part of any project. I mean, if there's infinite time, why prioritize? We can do it in the future, right? Why fix this thing? We'll do it some other day. It's like, there will always be a next release, Why should we commit to anything? Why should we say this is the thing we're doing when, we can change, We'll do a little bit of this and a little bit of that. Let's not make any decisions, right? We just ship it, right? We'll ship it. We can fix it in the next patch, who cares, right? What if the software did something completely different? Maybe we should just change everything, And this keeps happening. Like, this mentality breeds bad software, right? And it's not just like people saying, oh, it's management fault, but like, I see this from a lot of software developers. They're like, I'll clean this code up when management gives me time. And it's like, no, finish your software. Like,
I heard many different kind of cases here. They are very, those are completely orthogonal things, like finishing your software. Like, I'm not sure if he means being feature complete or bug free or high code quality. Maybe I'm pausing too early.
if you show something to a manager that looks done but is garbage underneath, they will look at that and say it's done, and they will do the next thing. They won't say, well, obviously everything looks perfect, but it's garbage underneath, and I'm going to give you a bunch of time to fix your thing. Like, when you show something to a manager, if you're employed, that's the thing you're delivering, right? Either you have to have a manager that understands you, actually go through the code and look how terrible it is, but if they can't see that, they're trusting you, right? It's like being Bernie Madoff saying, like, well, we lost out on, profits this month, but let's not tell the investors because we'll make it up next month, right? And we'll smooth it over, right? And then 10 years later, everything's like, why is this a house of cards, right? So it's not management fault. A lot of times it's our fault as well.
You just said it's a management fault.
Oh, we can't build like similar things. We live in a complex world where things are changing and requirements change and yada, yada, yada. Having hundreds of people simultaneously redesign a system does not scale. We can't have everybody working on a huge thing at the same time, developing in every direction and think that it works. There's a reason big software project fails, right? That is the point. All software should be possible to be written by one person. And I used to say this as sort of, here's my thought experiment. What if we did it this way? And the more I think about it, it's not a thought experiment. I actually believe this. I actually believe that there is no software in the world that one person can't write, right? Because if it isn't true, imagine the world where it is true. Make it true. Right?
Kernel.
Break it down into its components, right?
Browsers.
So can I get an example of like a really large software project that a person couldn't do? Can somebody think of something's too big for Chromium? Great. Okay. So obviously you could say from one point of view, you could say, well, the application is very simple, right? So if you have a widget that draws HTML, you're good, right? Somebody should just be able to do that. Anybody can do that, right? Or you could break it down from another point of view, saying, well, all you're doing is curl, right? And then, that's all you're doing, and then people can build on top of that. Or maybe somebody does a rendering engine. You can make it into a bunch of components, and then it works, right? Any other examples of hard software? Yeah, well, people are making AAA games today alone. I mean, I've always made one myself, almost, but people are doing it in Unreal, right? People.
This is skepticism
that look
of
AAA
from
because
me.
they have engines that exist, right? So you can always break things down. And the way we should communicate with each other is over APIs. Because humans are very much like CPU cores. We are really productive and really good until we need to synchronize with another one. Then we become incredibly slow. So you really, really don't want to synchronize.
There is some truth to
if you
that
can
statement.
avoid it. And APIs is the way we do that, right? I've met a lot of people that have trouble working with the person sitting next to them, working on the same project, but they're happily working against an API in, Linux that they've never met the people who've done it's just a document in API, and they use that, and they use someone else's code, and it just works, right? There's no questions. Everybody's like happy. But working with Bill sitting next to me, that's like a nightmare. We're fighting, and it's like trampling over all over our code. And I have this expression about...
I wouldn't be surprised. I'm not envious of Bill.
Building a mountain, right? You want to build up new things so that you can build on top of them. And here's the example of how I think about this. Have we gone to the moon? Mankind has gone to the moon, right? We've been there. But can we go to the moon? Well, in theory, we could go to the moon, but if we were to go to the moon, we would pretty much start over from scratch. We don't have any Saturn V rockets lying around ready to be fired. We don't have a moon lander sitting in a, shed somewhere. We would have a couple of really old dudes we could ask questions from, and they would say, well, in our time, we use computers that, run 1 kilohertz or something. So it wouldn't be very useful. And this is really what's important. Thinking about accomplishments versus capabilities. When you're writing a software, when you're writing software, are you gaining just an accomplishment of like, I made a game, I made a text editor or something like that? Or did you gain capabilities? If you make a text editor, you should gain the capability of doing text rendering really, really well, so that you can go off and do something else and you don't have to think about text anymore because you have conquered that. That is now a capability, right? Problems, solve problems so that they remain solved. Like a great example is like if you've ever done network programming, you start with sockets and you have all these structs that have fields that are called things, and there's flags, and you're like, okay, I have to look this up. What is the thing? What flag does I have to set up? And you try to focus on only getting the thing you need for your project. We'll go through all of them. Make a wrapper around that so you never, ever have to look up that documentation ever again and say, okay, networking solved. I have libraries for that. It does everything I wanted, and now I'm done. This is how you can go much further, because only, here's my best example of this, right? People say Apple made the iPhone. Well, Apple had made a whole bunch of things before that. They had made iTunes. They had made, they had a proper OS kernel. They had a desktop compositor. They had OpenGL. They had a Safari. They had a mail client. Right? All of these things they built over the decade before the iPhone came out. And then one day they can say, okay, we can make...
It's crazy that this motif is the same motif from the video he did 10 years ago. About the previous video he said about QuickTime.
Make the iPhone, because we have all these features.
Same argument though.
And a company that hadn't built up these layers of capabilities wouldn't be able to build this product. And the other thing is you want to keep your context windows small, because just like CPUs, we're bad at context switching, right? If you constantly have to jump between different problems, you'll be slow, right? You want to solve a problem so you don't ever have to think about it again. And your mind can really only let go of code once it's finished. And it's not just good enough. And it doesn't just have to be good. It has to be so good that you don't want to revisit it. You know that, like, I went into that and I went so deep and did it so well that I'm never going to be able to do it better. And I actually have a problem with this. I don't have a not invented here problem because I've invented everything here. Like, I have a source you know, I have my own UI toolkit. I have my own platform layers. I have everything, right? So I don't ever have this problem. What I have is not invented here recently. I have a like, yeah, but it's been 2 years. I'm a better programmer now. I can redesign this, right? And that's why you really, really have to push it and be like, no, it can't be done better. Or it's like, the gains are ridiculous, right? It doesn't matter, right? For this to work,
Rewriting base libraries is very hard, especially if you change API. Like, essentially what we're doing right now. I just decided that we will split objects and widgets, I mean, not just a couple months ago, and we're still dealing with the fallout.
your software extendable, and there's multiple ways of doing that, right? You build your software on top of other people's, right? Other people's work. Even if you're writing your own operating system, you're building it on top of hardware other people built. But can people build on top of you? Can people reuse the code you're using? And can your software be combined? Like, can you pipe data into it in a Unix command? That's a very simple way. You can have in and out and use your software in a chain, right? Or maybe, you know, you have your own API that people can call. Maybe you're a library. Maybe your software has a plugin interface, right? Don't impose your conventions on your users, right? So I see this a lot of like, you know, especially C++ programmers. They build big structures and it's like it handles everything. It has a thing and you have to have a handler and a thingy and a callback and a thing and then you can plug everything into this. And you're like, no, don't do that. Like make something that is easy to, you know, use an API that you can use that doesn't tell the user that they have to live with your worldview, right? That's why I don't like things like memory allocators. Like, I don't care about your memory allocator. You can use your memory allocator inside of your library. Like, I don't want your vec3 because I don't want to move all my values into vec3s, right? I just want, it's okay with a function that takes 3 floats. It's fine. Don't force me to live in your world, right?
Yeah, actually functions that take floats are a nice idea. I think there is some convention even for passing the floats, not sure of that, but maybe they can be kept in the... Yeah, I'm not sure actually, I'm not going to say.
And build utilities for a lot of things. Let's say you make, you make a format like a JSON format, right? How do you get other people to use it? Well, maybe the JSON format is super simple, but if you have all these tools that allow people to do it, maybe there's a Python interface, maybe there's, you know, a visualizer, maybe there's a UI for it, maybe there's a validator for it. Wow, then people want to use it, right? Make it easy for people to use it by building utilities. And this is not always true, but I tend to think that you want to build software that other people can plug into their software rather than having their software plug into yours, right? Plugin interfaces can be great.
Yeah, libraries are better than frameworks.
Somebody else's world.
This presentation is such a mishmash of everything. It's like I don't even know what's the... I mean, there's the title of the presentation, but we are digressed so far that...
under their...
I don't even know how it's related.
Generally, people don't want that, right? And the thing about this is that in order to stand on the shoulders of giants, giants have to stand still, right? You need your development to stop so that other people can start doing things. If you change your API every day or like, oh, you know, this switch here now means something different because it's smarter, it's better. It's like, doesn't work, right? Collaboration works when we can depend on each other. This is really important. You have to build trust so that people trust that the software I get from this person really works. And how does software work? Software is built, trust is built over time, right? You won't trust my software until you've had it for a while, right? And therefore, I'm really arguing that people need to build dependable software. And I would argue that the worst disaster that has ever happened in software is probably this, right? And it's like, people were like, well, Python 3 is better. You know, a few engineers...
I think it's good that it happened. The new Python is way better than... They managed to clean some things. Probably the reason Python is where it is today, which is like the second most popular language on the planet, is because they've done this transition.
Years at Python said that, and then untold billions of dollars had to be paid by the...
Compare this with other languages, which kind of stayed with their flaws. And you can look at the top lists of programming languages. Python is probably above them.
World who were relying on Python 2 to upgrade because they were like, well, it's nicer when the prints have parentheses around them, right? That is really what the world needs to spend billions.
It wasn't such a big change. Not only print, there were a few more changes, but none of them were major, really. Those are just small syntax updates. Strings became encoding aware.
Billions of dollars on, right? And this is really terrible. And that's why I think stable ABI is the most underrated feature of anything in computing. This should be our North Star, right? And there's a lot of, but this one is newer. Yeah, but this one works. That's always more important, You should always, if I've had a software run on my computer for 15 years and it hasn't crashed, and you give me a new version, which one do I trust, right? If you're gonna get on a plane, and you have two options. One is the latest plane that came out of the factory, a new model, #1 on the factory floor. It has all this most modern safety equipment, the most modern safety standards, everything is new about it. And then there's another plane that is, 20 years old. That model has been flying for 20 years and it's never had a crash. Which plane do you trust? I know what you're thinking. You're thinking, which one is a Boeing? So change is a huge cost to your users, right? We've all been there, where the fuck did they move the button, right? And some UI designers well, it's much more nicer now, and the aesthetics, and it's we don't care. We don't care about your software, we care about our work, and every time you update, you force me to update your software. I have to stop thinking about the things I'm working on and start thinking about you. It's you're not helping me now. You're stealing things from me, right? There's a great movie called Pirates of Silicon Valley. It's a TV movie about the birth of Microsoft and Apple. And I really, really like this movie. And there's a scene at the end of the movie where Steve Jobs realizes that Microsoft has stolen all their ideas pretty much and made Windows, a copy of the Mac. And he has this huge outburst, and they fight over this, and and then Bill Gates leaves, and as he leaves, Steve Jobs says we're better than you, we're better, and Bill Gates turns around and says, you still don't get it. That doesn't matter. And I think about that scene a lot because, as creator, we think, well, better is better. It's got to win, right? But a lot of time that's actually not true. Because people care about other things, right? And this movie is really hard to find. So if you ask me afterwards, I do not have a pirated copy on a USB drive. So the stable ABIs are not cool, right? It's really fun to make fun out of all the old crappy, Windows APIs. They look terrible and we can laugh at them.
Old Windows APIs are amazing. Nobody criticizes them. They are the staple of good API design. They are used as an example of good API
design. I can't believe they still have this. But you can run software from the 90s on your latest machine and it will just work, right? Yeah. And this is the reason why Linux has never broken through. Linux, the kernel has a stable ABI. Linus Torvalds, awesome guy, he gets this. But all of the distributions, they're but this is a newer one, right? So if you release a piece of software, a binary for Linux, it's not here's my Linux release. It's here's the Ubuntu release for this version of Ubuntu. And if you have anything else, you're screwed, right?
Yeah.
And I'm expecting that if any of the Linux distributions ever put their foot down and say, we're not going to ever break ABI and we'll not accept any software that breaks ABI, that Linux distribution will just win. People will say they are old.
The reason it works on Windows is that you always ship your libraries together with the software. You just don't expect the libraries to be present on the user's machine. And Linux distribution optimize this and provide the libraries themselves for the users. Which means you have slightly different builds for every distribution.
And people say, you know, we don't like you, but they will win. That's my pretty hard guess. So, and I believe in a stable ABI also among friends, right? We can talk about Microsoft being a big platform. So I have 2 employees. I pay them. I am the boss. I own the company, but I cannot break ABIs for them. I wrote an engine and they're writing games in that engine. If I made a fucked up API call and I realize I need to do it, I have to write a new API call and then I can tell them, when you have time, start using this one instead. I can't tell them, you have to drop everything because I'm going to break your code, right? I have to be, you know, for them to use my code, they have to trust me. I have to, you know, and that might mean I have to write a wrapper. I might have to, you know, if my code becomes uglier because I do that, that's my problem. I messed up. My ugly code is my problem, not my user's problem, even if they're sitting next to me, even if I'm the one paying them. So dependable software requires a different mindset. We have to think differently about how we write software. So the obvious one is only use dependable APIs, right? We want to use APIs that we trust, and we want ideally not to have dependencies. If you have dependencies you control. Are they compiled in? Are they part of the source code? You know, or are they, you know, the operating system you can trust? Don't tie yourself to any platform. Lots of people do that. Like people today build software that like relies on a web service being online. You know, that's like not very good. And when you rely on things, wrap those APIs, because you don't know. Microsoft may blow up and you may want to go somewhere else, right? So you want to have everything be portable. So even if you require some platform-specific things, you want to be able to move away from that at any time. Language-wise, I want to use something I call dependable C. So what is that? So I'm in the C standard board. I make language, or I'm supposed to at least. And I had this sort of idea, which was that I use C89, and I've used C89 forever. And obviously, we can all have arguments over, you know, what a language should be. Let's imagine that the VG14 was like, oh, Eskil, you're so bright and so special. We're going to defer all decisions to you, and we're going to write the standard exactly the way you want it. You can make all the changes you want, and you'll have the perfect language, right? And I'm a pretty hardcore advocate for old school C, but I in no way mean that old school C is perfect. It isn't, you know. So I thought about that, and it's like, okay, let's see, you know, this magical Uber Eskil C now exists, and let's say that the major compilers were like, oh, well, of course we're going to implement that. Would I use this? And I realized, no, I wouldn't. Even if I got everything I wanted, even if it had my name on it, I wouldn't use it.
No.
Because guess what?
If it was something like Odin, or I think many C programmers would like to switch something more sane. C also has its rough edges.
I want my code to run on anything. I want my code to be readable by anybody. I don't want you to have the latest version of anything. Being connected to the world is much, much more important than whatever feature I could get out of it. There's nothing in C that I can't fix with 5 lines of code. I'm promising you. So I think of languages as a storage container for instructions, right? We're putting down our time into something, and that is what the value is. It's like if you do work, you want to store that in money that is going to last, right? And C is really, really the gold standard. I can guarantee you that if you write in C89, your code will be compilable in 50 years. There will be a compiler for the supercomputers we have back in the future. It will work, right? And that's more important than anything, right? Because really, value is you make something that does something over time, right? If it breaks after 2 years, then it's half as valuable than if it breaks at 4 years. And with C, you can make it last for 50, 100 years, right? And even C is so simple that it's the first thing you implement on any new platform, right? You can even, if shit hits the fan, you can write your own C compiler.
Not necessarily. I think recently, instead of implementing C, people are implementing LLVM backends. Because LLVM backend is easier to implement for a new platform, and it gives you access to a much wider array of programming languages.
For your own home-built.
And it's also pretty well documented. If you look at LLVM documentation, half of the documentation is for backend implementers.
Hardware, and your code will run there, right? That is not true for almost.
And you do this, and immediately you get languages such as Rust, C, and C++, and you can mix them.
Almost any other language.
So this is not true.
I don't think of a language as a tool. A lot of people talk about language features. I don't want the language to solve my problems. I like debuggers. I love, tools around it that operate on my language. The simpler my language is, the better my tools are, right? Because the easier it is to build a tool, right? Everybody knows that it's like a simple file format everybody can make use of. If I make a complicated thing, all the tools will suck, right? So I love this. This is a little bit old, but this are all the operating systems that curl runs on. And it's actually over 100 now, because I couldn't find the latest slides. So Daniel Steenberg is the credit for this slide. But you can't do this in anything other than C89. You can't do this in C99. And sure, you can get a lot of it in C99. But if you really, really care about being understood by everybody, this is where you should go. And this is kind of interesting. If you ask people I want to write this piece of software, how should I do it? Generally, people say, oh, you should use React, or you should use, this new language, or this with this, system and these frameworks. And, they pile on these, oh, I just read about this new technology that will do this, right? But then you ask them, it's I have solved this problem. What do you wish it was written in? And it's everybody's oh, please don't come with a bunch of, a huge C++ thing, or, some weird Haskell. Come with a small C library in C89 with nothing in, no dependencies. That's what you want to integrate, right? When I made the UVN wrapper, I went to Maxon, and Maxon's, all their software is C++, and I said, well, I'm sorry, my software is not C++, it's actually only C. And they were like, oh, thank God, because we like being in C++ for ourselves, but we don't trust other people to write C++. God knows what, C++ interfaces, you can't trust that, C, that's fine.
And there are plenty of good C++ libraries, but it's true that it's very easy to abuse the language. I wouldn't worry. Skia is C++, right? Skia is excellent.
Fine, right? So think about that. You don't.
And Skia avoids advanced
if you have a lot of
C++ features.
syntax sugar, that might be nice for writing it, but for using it, it's I don't want syntax sugar. I want performance, right? Syntax doesn't solve your problems. And I'm kind of think that convenience is very open.
To some degree it does. It forces you to follow some protocols often. Type checking is part of the language syntax. Borrow checking as well. The constructors and destructors are a convenient feature to have for safety.
Overrated, right? I think that the convenience you get from a lot of higher level languages really just, hides things, and it makes it quick to get off the ground. But in the end, you're going to want to control that. In the end, you're going to want the software to be super, super fast. Typing is easy, right? Typing is not the problem of programming. I'm the worst typer. You can check me out on stream and laugh at me if you think typing is important. Code is meant to run, and I think one thing that struck me was I was reading an FAQ on the Linux kernel, and this is like, why does the Linux kernel have a bunch of go-tos? Isn't that really ugly? And the answer was like, it generates better assembly code. The Linux kernel is an engineering project meant to run. It is not meant to, you're not meant to read the source code. You're meant to actually use it, So when you create a piece of software, here's my model for how I create software projects and how I try to finish them. So I start out with a plan. Usually I have a couple of software projects in my head that I haven't started on, and maybe even not decided whether or not I want to do, right? But I'm thinking about, what the structure is going to be, and, and I let that fester for a while. Then I write sort of 80% of the code, right? Because I know what I want to do. Here's, the majority of the thing. And then usually I make parts of that as libraries, right? So that like, oh, this thing I need, a lot of times this is part of sort of the project. It's like, I'm going to write an editor for text, but I don't have good spelling thing. Okay, let's build a spelling library. I can use a spelling library for a lot of other things. Let's build a spelling library, So you sort of have these sub-projects that you finish. And actually, you could sort of look at this recursively, because the structure of the project that I'm showing, you could actually shrink that down and put those in the green and the blue box, because I kind of do the same thing. Then after that, I do a lot of revisions, because once you get to like 80%, then you can start using the software. And then you realize it's like some of your ideas weren't perfect, and some things are a little bit fidgety, and so you have to make another sort of thing. And you can do that. You don't have to finish the application to do that. You can just tell that like some of my assumptions weren't that great, so I need to do some revisions, right? And then you get to sort of 1.0, right? And then after that, you do a bunch of revisions where it's like, oh, I need more features, I need this and that. And then you can see they start spacing out. It's like, and if you think of this as a library, it might be like, the beginning, you're like, oh, I need these features. And then eventually, very seldom do you like, oh, I'd like another version of this function that does this slightly differently. And then I'm done. Except now I start planning. If I want to do a second version of this application, let's say I want to do 2.0, I start over. And a lot of projects, I just wipe the project and start over. And an example of that is the lighting software that I've written. This is Stellar 1.0, and here's Stellar 2.0. And those two applications share none of the source code. It's a complete wipe. I have all the knowledge. I knew all the things that I did wrong in 1.0, and we're able to refactor and restructure everything.
You mentioned the platform library, for instance. So is he not reusing it?
Each one of these took about 9 months to write. So, but then the cool thing is, hey, the blue and the green box, I can reuse them, right? So I'm not actually starting from scratch, right? I can actually, have a completely new design with a completely new paradigm, but I don't have to reinvent my font rendering, right? That doesn't matter, right?
No.
Right now, I'm working on a game engine, and this is kind of what it looks like right now. So the game engine, actually, the majority of the game engine was written in about a week and a half. But then I've written a geometry library that does like collision detection, it does full destructibility, pathfinding, and a lot of things like that. And now I've been working on my serialization library. And as you might see on the size, I've sort of went overboard a little bit. So the serialization is a lot more than you need for my game engine. But it's going to be awesome, I think, if I can finish it. And this sort of permeates a lot of software. So I want to introduce you to my favorite games of the last couple of years. This is Battle Aces. It's a strategy game. It's awesome, except you can't play it because the economics of finishing software is terrible. So originally we had this idea that we would, the amazing thing about software, you could develop a software product and then you can sell it an infinite time. Isn't that magic, right? It wasn't like, building a car and when you sold it, you had to build a new car to sell. That's expensive, right? And software was amazing because you could develop it once and then just like sell and sell and sell. And you get things like StarCraft, right? StarCraft was released in 98 and there's still professional tournaments being played. The game is still selling. And shouldn't this be the goal of all of us? Right? Just create something and then have it live for 30 years and just like being resold and loved. That's what we want, right? The problem is that people looked at this and was like, oh, this is nice, but infinite repeat sales, that'd be nicer, right? What if we make it subscription? Or what if we... And the problem with this is that once you get into this, you also get into this, repeat development. We have to justify that you pay us every month by new features, by changing things, right? And the problem here is that the game I showed you, Battle Aces, was built under this model. And they basically run it in a beta, and they realized, even though the game was perfectly finished, that these two numbers weren't going to correlate correctly, so it's canceled and dead, right? So instead of getting a game we could all play, we now have a game that most of us will never get to play, that was buried because, they had the idea we're going to make a game that we never finish, and therefore we have an infinite cost of development, and therefore we need to have a lot of money coming in the door. This really sucks. So therefore, I'm asking you to ask yourselves this question. When you release software, would you be fine with it being your last release? At least if you've gotten to 1.0, like, is this a thing that is just a bunch of holes where you're hoping to fix it later? Or is this something you're like, if I get hit by a bus today, people will be proud of my software, decades into the future? So I didn't really have a good ending, so I'm ending here. Here's my contacts, so you can find me on Twitter and Blue Sky, and that's the website for my company. And come and follow me on Twitch. Thank you very much.
Now there will be, I think, a Q&A session.
Då var vi här.
Då var vi här.
Ja, härligt. Så maybe we should switch over to English, but we could do this in Swedish, right? Wow, I too have a lot of unfinished projects.
Yeah.
I have a lot of them, and it was amazing listening to your talk because I was like, wow, there's this why doesn't people do this? Because it makes so much sense. How do we get so far from what makes sense?
I don't know. Yeah, it's weird that I kind of have to give this talk. It's something I found a lot with my own development, that it's like, right now I'm working on Marshall, which is my library for storing data and serializing data. And it's like, serializing data is kind of easy, right? It does, and therefore it's really easy not to use a library because you can just write a few lines of code. Why should I bring in this massive project to do that? Well, it has to be so goddamn good that I get so much out of it that I will actually use it. And it has to be so trustworthy because I can't debug it, when I'm using it. It has to be so rock solid that I trust it. And right now I feel like it's not good enough. I'm never going to reuse this. And I know I have to push it over the edge of being, I'm trusting the software and I will use it forever. Because there's libraries I've written that I use for everything, and there's libraries that I've used once and never used again.
I really like this because one thing I like this not invented recently mentality. That was like, oh yeah, I go back to this piece of code and I'm like, I need to fix this. This is not recent enough, or this has become out of sync with what I know. But if you build it that great that you kind of can put it behind you and you can like, yes, this is actually done. I can
Yeah.
actually depend on this because
Yeah.
it's stable and I know what it does and I understand it. And I can then I can continue.
And also, it's like sometimes if it's like a little bit over-engineered, you're like, I went to such great lengths.
The
with
code
this.
completion is excellent
So,
here.
like things I do is like, okay, you know, you have a key value store, you have to compare a string to, you know. So the thing I do, for instance, is I guarantee that all strings are at least 4 bytes long. And that means I can do the beginning of the compare with the 32-bit compare instead of doing individual bytes. And it's like, that's a little bit too much. I wouldn't do that normally, but it's one of those things that's like, yeah, I should use this code. this code has really been optimized, and you know, so yeah.
You said that you don't think about languages as tools, and there's so many different. Like we have a lot of languages showing up, and people are trying to solve problems. But
Yeah.
but your approach is more, well, we're going to use this to build something, and really we don't need much. Like you have, like I appreciate some of the C99 features, but you draw the line before that.
Yeah, so I do, for a couple of reasons. First of all, I really don't need anything in C99. C99 adds VLAs, which I think are really broken because they're basically a way to allocate memory that can't report that it's out of memory. And it allocates this from a stack, which is between...
It can't report an error, but you have some control over this. You can, it depends on the operating system. If C just had an API for asking for the right, there is a Linux, it's called break. BRK syscall. It allows you to tell how much stack you want to have. But it's only on Unix. I guess Windows has something like that as well. So it's just not standardized.
1 meg and 8 meg depending on your operating system, and that's not very much memory. So it's a really dangerous thing. So I think that's one reason, but it's also other reasons. Like I think C89 is slightly more ordered, and I also think that I want my code to be readable by like C++ people or people who are not like... C99 is like for C programmers, whereas C89 is for everybody. I'm actually trying to put together a website, dependablec.org, where I document like what's dependable. Like if you want to write code that lasts forever, you shouldn't use a bunch of features, but then there's a bunch of features in C89 that are not really trustworthy for various reasons, or like, you know, the things that are technically legal, but there's a lot of bugs in compilers around. So there's a little bit of sort of a fuzziness around it. There are things that have been deprecated. So, you know, you want your code to run even if you don't explicitly say this is the version that I require, right? You want to just like default setting, run the code, and it works.
You would know because you are writing the book on UB.
Yes. That's a really exciting area. So yeah.
So maybe we should open up some questions from the audience. Like, let's go, Rafael.
So you're on the C Senate committee, but you stick to C89. I assume you haven't been on the committee in 89, so you have never actually used anything you've done in the committee?
That's correct. I don't intend to. That's kind of the thing. Is like, for me, C is valuable, or the most valuable thing about C is that it's everywhere. Everybody understands it. It's stable, and that's more important, right? So I'm in the C standard board to protect that, right? It's like, and everybody has opinions about what's wrong about C, but it's like, to me that doesn't matter. What matters is that it works, right? And the problem with the C standard board is that they're all really smart and all really well-meaning. I don't really have bad things to say. The problem is, why do you join a language design group? Because you're a language designer and you want to design languages. And that means that everybody wants to add something, right? If you have 40 people in a room, everybody agrees that C should be small, except for the feature I want to add, and you have 40 people, and then, you know, you get a bunch of crust, right? And I think fundamentally, there are problems in C, but you don't need language to solve that. And since C is backwards compatible, it sort of becomes a little bit of a weird issue where, like, okay, you should use secure memset instead of memset sometimes, right? But only the people who know why memset isn't secure know to use secure memset, and the people who know that memset isn't secure know how to get around it. So you're sort of adding a feature to fix a thing, and to explain why the feature exists, you have to know the problem, and if you know the problem, then you don't need the fix. And it's sort of, you know, if you could remove memset and make it safe, you know, then be different, but that's not how the world, you know, C works. So that's why I actually don't vote on C2Y, which is the next version of C, because I would just vote no to everything and everybody would just hate me. And I don't think I have, like,
Absolutely.
I don't go in and vote on C++. Like, let them build whatever they want. Like, you know, I'm pretty hardcore on C, and I want to protect C, and I think that's important that we do that. But if people want to go build Rust or whatever, everybody should program whatever they want. You know, I'm advocating for what I think is good, and I think people should consider it. But if you don't agree, that's cool, right? You not agreeing with me is like, that's how I learn. So, you know.
You got it, and you have it.
Yeah,
Right.
I got the language or a good enough language. It's like, I don't care, right? It's like, yeah, there's stupid stuff, but like typing is not the problem, right?
One of the things I wanted to poke at a little bit is you had mentioned that code is meant to run, and so things might be obtuse for a reader, but they might actually be the best thing for the program, right? One of the nicest things about C that I find is that it's kind of a common ancestor of many languages, and so it's sort of the thing that most people are able to understand, the kind of common language for code. And so I particularly like that if I'm writing a piece of code, even if somebody doesn't use that code, they might come across it, read it, and know where it would apply to their thing, and take the pieces they want, make their own version, that sort of thing.
Yeah.
What is your opinion on like that sort of sharing, where it's like it's not actually,
It's very universal, yeah.
it's not done, right? They didn't use my thing off the shelf, they went and made their own thing, but the like concept is
Yeah, and I think I do that myself. You know, I don't copy code from anybody, but I hear ideas from people, and then I make my own thing out of it. So I think that's great. But that's one of the reasons, like, I don't like macros. I use very little macros because I don't like looking at code and it's like, oh, here's a thing, and it's like the dude who wrote it thinks he's clever, but I don't understand it. You know, I'm much more in favor of if you want meta programming, just write a C program that generates C. You can debug both of them independently. You can read the output. Everything is clear. Everybody knows what's going on. I tend to want to ship the generated code and have the generated code be disabled because I don't want to impose, like, here's the build step you have to do in order to get my code to run. It's like the fact that I use generating to build part of code, that's none of your problem if you just want to integrate my code. But yeah.
Check in the generated files.
Yeah.
Yeah.
Well, I don't check in because I don't use version control.
Okay. Do you do backups?
Sometimes. It happens.
If you're not using version control, you have to do backups.
Yeah, Rafael. Or there's anyone else? No?
Absolutely.
Rafael gets it.
That needs a follow-up question. Why don't you use version control?
It's never given me anything. Like, I have, so the structure
So this is a controversial statement, but I do agree. Many people use version control as so there are multiple uses for version control. One of them is to coordinate work between multiple people and match changes. If multiple people do changes, the same thing in parallel, the changes have to be merged. It can be done without version control though. The only thing you need is this diff, this three-way merge mechanism. And with that you can have a central repository which is just a single version. Everybody can have their own copy that they work on, and they can submit changes to this using this three-way merge. Version control gives history, and this is another valuable thing, which is not necessary if you have backups. So version control is like backups plus merging of code. Except it's different approaches also have their own features.
I use is I have
Like Git is kind of fun and interesting on its own.
which is the merge of all my source. And then I name all of my projects so that the beginning of the name is the name of the project. And sometimes it's like a hierarchy. So if I have like subsystems, they're named. So you can look at the file and just see where things live. I use the same names for the functions within them. So if you see a function, the beginning of that function is the file name where you will find it. It's all in one directory. I use, I develop on Windows mostly because of Visual Studio and the stable ABI. And what I do is that I have that directory in the same thing. I create a project. I go and select the libraries I have so that when I run a project, I always have all the files in there. I don't pre-compile libraries because I want to be able to do that. But that means also that I can have two different projects working at the same time using the same source libraries. And if I changed it in one, it will change it in the other. I can also do a search through this so that if I rarely do this, but if I need to change something, like in a library, I can actually search the whole source code and see where's that used. And I'll see all of my projects where it's used. So, and that's really all I do. I have a directory where I tend to put deprecated stuff. I tend not to delete files. What I do is I put an if-def deprecated around it, so the source is still there. And
Interesting.
the reason for that is
Yeah.
if you have a directory with your files in two different computers and you copy them forward, and then you delete one and then you copy and it's still there and it comes back and you get these zombie files. So instead I just keep it and just like if-def it out.
Yeah, Sam.
Another follow-up. So could it be described more succinctly as you have a mono repo with your entire life's work, but no history?
Yeah. So every once in a while, I can do a sip of that and put a date on it. So I have some, I could go back, but I honestly can't remember when I ever have gone back.
So there are backups. Zip with a date is a backup. Okay.
Quick note, his mono repo is available online.
Oh, wow.
You can go and check out all of his code.
You can also watch Eskil manage all this live.
Yeah.
Every day between.
Yeah. It's a nice way to organize
Usually
code,
like 10 in the
ironically.
morning until just before 4
Yeah, Swedish time, I guess.
Swedish time.
Yeah.
Yeah, longer on Tuesdays.
Masha?
Also follow up. So, and junior programmers who work for you now, those guys, they also put their files to your repo, or they do their own repo. Like, how do you manage that?
So basically what we do, and so with the lighting, I was CTO with a lighting company. So I've been working alone most of my life. So I haven't had to deal with, it's a little bit weird to be in this conference, to be honest, because it feels like being in an AA meeting for like object-oriented survivors. And there's like, oh, I made it out, and I was like, I was never in, right? It's like, I never gave a shit about that. I'm just like born C, still C, always C. So it's like, but so a lot of people have said like, well, you're alone. This is never gonna.
Yeah, orthodox approach to software is just it's very limiting. You will never do as good job as somebody who just picks the best technology to do the job.
Gonna work. The way I've worked in the past when we've had team is basically we make our own, everybody makes their own projects. So either a different application or different libraries. And you work on your own machine, you have your own version, and then you make a release just like you would release software into the world. Just like you would, upload a new game, you basically say, okay, this library is now done to this level. I am now giving it to my users, which is the other people. The other people in the team are then free to ignore that because they might be busy doing something else, right? It's just like something that is available if you want it, right? And a lot of times people are waiting for things. They want things, but not always, right? And therefore, internally in a studio, we work as if we are, independent software companies that release software, and people update when they want to update.
Yeah. Okay. Yeah. So Ben.
You noted that a stable ABI is the most underrated thing in computing. What are some of your favorite stable ABIs, and what would you recommend we use more?
So there's like 1.5 out. So it's like Win32 is the stable ABI. I mean, it just is, right? And I mean, Windows has like special code in Windows 95 to make SimCity run, because SimCity on Windows 3.11 did something weird. And Microsoft was like, what the fuck are these guys doing? Well, that's our problems, because it worked before, it has to work now. So they wrote special code in Windows in order to be able to have SimCity run, right? That is what a really, really trustworthy platform holder does. There are no others that I know of. There's like the Linux kernel. So you can build a stable API, system from a Linux kernel. Nobody's done that. Apple is terrible. They break things all the time. They just like, but this one's new, They're like, they're worse than that. They're like, oh, you should change your programming language. Rewrite everything in this new language now. That's like their approach. I think you could, curl has a stable ABI. Those are, curl lib. I would say, who else? You could argue that the web is a stable ABI, right? People write really shitty HTML code, and the browsers do their best to make that work, right? The browsers have so far never said, oh, these web servers are too old, we're just going to show a black screen, right?
Trying to answer this question, it's actually a very interesting question. I guess there are some systems which are designed to be append only, so that once you have a piece of code that works, you do not change it. You can install a new version, but the new version which doesn't invalidate the old one. I guess there are a few systems from this category. Some software repositories, I guess, are like that. Unix, the platform, is a little bit like that. Some programming languages exploit this natively. I think Unison language does this. Valtown, possibly. I haven't tried Valtown yet, I should. There is this whole online visual programming called Valtown that also works like that. They definitely have stable ABIs, and the stable ABIs are pretty much enforced because you cannot change code that you submitted already.
Right. That does not happen, and the web was never planned for that, which is one of the reasons it's such a mess. But you still got to give them some credit for upholding that. So,
how are we on time? Yeah. Okay. Cool. Just on the ABI issue on Linux. I am under the impression that the C ABI is the ABI for the Linux, but that's not true.
So you have the kernel, which is the kernel, and that has a stable ABI, and you can search for like
C is a
Linus
little
Torvalds
bit-
rant
I mean-
stable ABI, and he will.
ABI is used in a couple different contexts, and it means slightly different things. For Linux, syscalls are one stable ABI. glibc, this is a very specific C library, which is the most popular on Linux. It tries to offer a stable ABI, and they do a relatively good job at this. They're putting a lot of effort to make this work, and this is why we can still run old software for Linux on new machines, because glibc offers this stability. I think a lot of those issues would be better solved with static binaries, but we are where we are, right?
Will scream at people. It's like there's only one rule of kernel development: you do not break user space, right? So those are really fun. And then, but then there's the glibc, or the various C-libs that implement malloc and all of that, and those are not stable. People change them all the
glibcs.
time, and those break. So even if you write like the simplest C program that doesn't do anything except malloc free and printf, you can still have your code be broken. So
Let's see. Yeah, Andrew.
So if I understand correctly, when you're dividing work between yourself and your employees, it sounds like you're setting quite a hard boundary up front, and everyone is basically building their own library or building their own application and then connecting those together. Do you find it difficult to decide where those boundaries should be up front, or have you ever had to change where those boundaries are at a later time?
not really. Yeah, it's like, think of it as like delivering an API to somebody, right? And I mean, right now we're starting out, so I see my employees as my customers, right? I've built them an engine with an API, and they're supposed to be able to make a game in it. And anytime they have trouble doing that, I'm looking at myself, say, can I make it easier for them? Have I messed up? Should I change this? Should I, and that's kind of how I look at it.
In that kind of context, do you find that you change your mind about what should be in the engine versus what should be in the game? Or what you think are in which side of that boundary?
I think the engine right now is pretty light. I'm expecting us to maybe build a project in the future that is like a standard library of features that is not in the engine, but that, for developing stuff in the engine, possibly. But I can also imagine, different developers in the team making their own mini standard libraries with like, here's the things I keep using and I want to use, and they may not share those with other people, or other people may not want to use them. So,
Sander, did you have a question?
Yes. I was wondering about the point of Windows being a stable API, and that being a positive point, versus Mac OS breaking stuff all the time, which is obnoxious. But today we experienced once again Windows crashing and Mac being magically stable for some reason. Yeah. Do you think those are related or not?
I think they're related to the fact that one of the companies have to care about their own hardware, and the other have to care about the whole world's hardware. It's like, I mean, Microsoft gets a lot of crap for things, and sometimes deservedly, but they're solving a very, very difficult problem. And I mean, they've gone through some like with Windows Vista, for instance, was a time when essentially the driver model was bad, so that DirectX 9 could only draw like roughly 50 draw calls per frame. That was kind of what you had, because every time you did a draw call, you would switch into kernel mode. And that switch was so slow that you couldn't really get more than 50, because you would just eat all the CPU from the switching between kernel mode and application mode. And they fixed that with DirectX 10 by changing the whole driver model. And that meant that everybody had to rewrite their drivers for Windows Vista. And that's why Windows Vista was a disaster. It was blue screening all the time, but that's because every driver for the computer was brand new, right? And then they basically re-released Vista as Windows 7 and removed some pop-up, and people were like, oh, it's so much better. Well, it was mostly just the maturing of drivers. So, yeah, I mean, it's easier being Apple, but like Apple locks you into like, Apple is great if you do everything precisely the way that some Apple engineer imagined you would do it. And if you have your own ideas, don't think different. Whoever said that, you know, so.
Okay, Taylor, go.
Interesting. I'm not sure if I can trust this opinion, but I never programmed on macOS, so I'm curious how it will look, because I am going to port Automat to macOS eventually.
So your talk is like that you want to finish software, right? And at the beginning, I think you had mentioned that like you feel like you have a software finishing problem, right? But by the end of it, I feel like that's not true. You have finished many libraries that you now like consider finished, right? And so I think the nuance there, right, is that you push yourself to finish the library, but maybe that is actually...
R618 says.
It looks like everywhere else.
You might suffer for the finishing of the piece that you want to wrap, right?
I would say I probably have...
I mean, it has the Objective-C. I mean, probably now it's more Swift than Objective-C, but it has some funky requirements. I remember at work we used to write software for iOS devices. It wasn't me personally, but I was close enough to see how limited was the technology choice for the people writing this software. They were, for instance, required to use the Apple's browser, right? So you couldn't run your own JavaScript engine. You had to use the JavaScript engine provided by the iOS, and that was enforced by Apple during the review process. You couldn't run any sort of dynamic code, because why would you? There are some reasons to, I mean, dynamic code meaning code that you basically JIT, map into memory and execute. It was forbidden. It would be silly if macOS also did it. Maybe mobile devices did this for security, I don't know.
At least twice as many libraries unfinished that as I haven't finished. So you may look at my public...
All things said about Eskil, one thing is really impressive, is that he made a lot of software. And when I listen to him, it feels like the standards that he's putting up, the very high expectations of software, are totally unrealistic. But the fact that he actually did this speaks that it can work. So this is really impressive.
Merge source is big, but my private is really big. So there's a lot of abandoned projects or like things that, you know, I didn't finish. So yeah.
Do you think that there are times where you would encourage somebody not to make a finished version of some particular library that is possible? Because the rabbit hole, in order to do that, right, that surface area, like the serialization library, for example, is that counter to finishing other things you can do, right?
Yeah, of course. I mean, you always have to think about what you're doing with your time. I think the problem I have right now with serialization is that I'm like 90% there. Right? And I need to put in the really hard, annoying last, you know, they say in game development that the first 90% is easy. It's the second 90% that is hard. And I'm sort of, I have the hard part done. And the thing I know is that
I'm actually very curious about his serialization library, because when you serialize stuff, you have a couple trade-offs that you have to choose. Whether you want the format to be readable by people, whether the software can be backwards compatible with new format additions, how efficient it is on the wire, can it be mapped directly to disk? Like if it's like flat enough, it can sometimes be mapped directly to disk. But I thought almost all of the combinations of trade-offs have already been implemented by somebody somewhere out there. So it's curious to me what trade-offs he's going for that are not, or maybe he's like re-implementing it just for the sake of re-implementing something. But yeah, let me quickly check. Mm-hmm. Okay, I guess this is Testify. No, it was 4 years ago. Last updated 4 years ago.
You use provided platform libraries and do your stuff. You ought to adhere to some guidelines, yes. But I don't find e.g. JVM engine limiting. Depends on SubU, the Obschrift you should use for UI native apps. You're not limited, e.g. for games there's C-apps games still being ported, etc. It's not one framework, especially now with transitioning from Obj-C.
That makes me a little bit less concerned. Oh yeah, he said that he... Let's go one by one. Mm-hmm. This is the 3D modeler.
People have wrong opinions formed often, but the limits by Apple are mostly social dollar related than technological now. E.g. Metal, the graphics system is widely recognized as superb compared to Vulkan OpenO, etc. But anyway, best to try do some stuff there. Xcode is horrible though.
We'll see soon enough. Looking forward to Metal. The rendering library that I'm using actually has some Skia, right? Skia. It has some features which are only present on macOS devices precisely because of Metal, like timing APIs. You can do more precise GPU side time measurements on Metal. I guess maybe you could do them on Vulkan, but on Vulkan, when I look at, I have two computers, like my desktop PC and my laptop. When I look at Vulkan extensions, there is basically no common set. Like Intel has their set of extensions, NVIDIA has their own set of extensions, and I can just guess what AMD has. So I'm implementing anything that would use extensions would be basically implementing it 3 times for different GPU vendors.
They are sufficiently different, yea?
I couldn't find this serialization library. If he mentions the name again, I will search for it.
Unless I get over that and get to the other side.
Yea,
the
I
90%
use Unity for those
is, like,
reasons.
flushed down. Like, it has no value.
Unity, by the way, I don't work in game dev myself, but my brother works in game dev. And recently, there was a lot of controversy about Unity, but he told me that when it comes to actually choosing, like going with some engine, he looked at Godot, and Godot still has, like, this photorealistic rendering in Godot is still kind of lagging behind. Unreal is just slower to work with, and Unity is, even though it's not, it's not the most popular engine online, and it's known for a lot of terrible games, you can make really good games in Unity if you just program them right. It's still a very good engine, and the asset store is amazing. Another controversial statement. I'm not in game dev. From my perspective, Unity asset store looks amazing. From the perspective of other people who work with it, they tend to complain. I don't understand this. I would just use this for everything.
But okay, WSU.
Value whatsoever. And that's
there is one amazing thing in Unity that I wish Unity was open source. They have in their APIs, there is a capsule raycast. So you can, given a primitive, capsule cast. Oh yeah, capsule cast.
It's from Fists originally, I think.
I've spent like a couple of days trying to come up with something like that. I couldn't figure out the math to do this. And it would be pretty sweet to have this. I mean, I was attempting to do some game development. I never really got anywhere, but Capsule Cast is like the ultimate raycast. If you have like a sword, for instance, in a game and you're moving the sword, this is a type of capsule cast. It allows you to detect all of the points that you will hit when swinging a sword. For developing game logic, it's a very cool primitive to have. And Unity is the only one I know that has it. Or maybe physics, like you say, but I'm not familiar with physics at all.
What's pushing me right now to get through it. But yes, I have other things to do.
Timothy.
Do you like throw away a lot of code before you like use it seriously in other projects or like publish it, or do you keep most of it?
I keep all of my code, so I don't.
Rick Crafter just followed on Twitch.
Hey, thanks for the sub.
It's not like a movie and you cut out scenes. It's like you just keep everything.
I do when usually.
Rick Crafted says,
"Hey, what's so bad?"
Hey.
Do the rest of the 80%, like I've changed things. So, I think the serialization is really in on its like third rewrite or something like that. But there's parts of it that are completely rewritten, but it's like you write something and you realize like, I should have designed this differently. You move back a bit.
How are you doing today?
Hey, doing well, thanks. I'm curious about this serialization library. Okay, I will search again. Serialization, please. Or maybe I should use his stream name.
Good to hear that.
And then you go again, and then, so you iterate forward a little bit. But then when I reach the end, if I reach the end, then it's pretty stable.
V tell you, I lurking around, actually I do Twitch custom graphics for the stream like PFP banner overlay emotes, VTuber.2.
I'm not interested in that.
Pretty much. I can give you an example. I have a network library called Testify. And Testify has been with me for a long time. And I recently wrote Testify 2, which is, because it was like limitations. But Testify 2 is not dependable yet.
Testify was the OpenGL wrapper, I think.
I still keep around Testify
Sure.
1 because all these software that I've written uses Testify 1, and there's nothing wrong with that. Maybe I want to update them in the future, but that's not guaranteed. And Testify 2 is not really, So yeah, I may actually end up in a situation where Testify 2 never takes off and becomes this failed project.
So this is like in large part for yourself, not just for like other people. It goes both ways.
I think it's the same thing, right? Because it's like, if I finish a library and I know it works, then other people can use it and know that this is a working thing. But it's the same thing for me. I can work on something else and not have to think about that piece of tech because it's solved, right? It's the same compartmentalization of just having something you can trust. And whether that is software you've written or someone else, or you're writing for yourself or someone else, it's the same problem, really.
Okay, Sam, you had a question. Yeah, we are out of time. Okay, then, ladies and gentlemen, mina damer och herrar, Eskil Hellstad.
Sweet. So the conference has more talks, but I think we saw all of the others. So this one specific, I have to say, it was pretty chaotic. It was pretty chaotic, and I think I said it after the previous video. In general, like stepping back, it's probably not a good thing to be orthodox when it comes to software development. Throughout the presentation, there were many mentions of object-oriented programming and nitpicks at that. I think this is largely strawman. I think people are imagining object-oriented programming to be some parody of object-oriented programming, and then because this parody is silly, it doesn't make sense. It's a good topic to make fun of. But have you ever seen this sort of crazy object-oriented code? I mean, you usually write it when you learn it, and then never again. So, in my opinion, everything in moderation, as who was it? Avicenna? This old Greek doctor said. Everything in moderation, right? A lot of the things, like especially, it's funny because a lot of the examples from the presentation, maybe not this one, the previous one, they used objects, with lifetimes that has to be managed, so deallocated. And I think it's convenient to let compiler do this. The compiler can do this at effectively zero cost. The compiler knows, for example, I have a mutex log. The compiler knows when it goes out of scope, and it can automatically unlock it for me. I don't have to think about this. The same here. Here I'm acquiring a smart pointer by doing the atomic increment, and the compiler knows that this closing brace should decrement this atomic counter and possibly free the memory. So, no reason not to use those tools.
Fry618 says,
Hey, B2D. Capsule. There should exist something at least similar to CapsuleCast already, I'd guess. Combine 2 spheres and 1 EQ for cylinder. But I think I've never actually needed to use CapsuleCast. Yay, scoped auto-destructors are okay.
Yeah. Maybe this capsule cast was kind of specific to my game because I decided to represent players as capsules. Literally as capsules, not invisible capsules around players. The players were just capsule-shaped bubbles. You can imagine in an environment like that, casting capsules could be useful.
It depends on the game, and what physics you want, definitely. I made roguelikes recently, so no capsules.
Ha! My game was a roguelike, and it had capsules. Yeah. I guess it would be nice to find more videos, but it is kind of getting late-ish today. So I think we will do more YouTubing on the next stream. On this stream we can probably finish the...
Good luck with the banner overlay.
Yeah. I mean, I just fixed the OBS settings, so banners should work nicely now. But yeah, I have essentially 5 layers on screen. There is the camera that looks at my desk. For whatever reason, I just have it, so decided to activate it. Why not? Today, I haven't used it before. Then I have the camera that films the room behind me. Then I have the desktop capture from my PC. And on top of it, there is some funky background removal overlay with just my face. And then there is bot with chat and everything. So many overlays. OBS is amazing. OBS is incredible. Anyway. Oh, and there is a gaze overlay, so when I'm looking at stuff, you can see where I'm looking. I'm almost done. I'm looking at the scroll bar. I'm here. So all of this part, the file was updated. It should work. I only have to fix the stuff on the bottom. I think it's okay to change some things instead of calling functions and getting a up-to-date value all the time. I'm now reading a cached value, but this cached value is actually cached while the widget is being rendered. So I think it's not going to cause any lag or any visual issues. It may actually make UI more accurate reading cached data here. Okay, I want to do that. Find the action. Okay, this current post ratio should just be there. Okay. Okay, here we have to do the funny locking. So honestly, I cannot imagine writing a code like this in... Let's see. Multi-threaded code in C, where I have different multi-threading primitives. I have those smart pointers that I have to manage. I need to lock the mutex. Yep. Still more errors. Yeah, it's not going to be a lot of code here. The music slightly louder now. I'm going to introduce a tiny static function so that I don't have to repeat this funky logic. Actually, shouldn't need this. I should be able to grab the parent. Yeah, exactly. Should I even cache this? Let's do one more thing. So we cannot hold an optional reference, I see. We do not need timeline, I think. We need. We should acquire a lock here. Because we are accessing stuff that belongs to timeline, kind of. The errors just don't end. Okay, there is nothing like that. And now minus started at is the same as TimelineWidget. Current offset. It's crazy, my only plan for the day is to finish this one simple refactoring. Simple. Now this is interesting. I want to notify the run button. That it should update itself. Do this. Yep. We just have to put this in a couple places. So if timeline was playing, then the animation should be updating itself anyway. And we are starting. I need to wake this. And this. Still more errors. It's crazy we don't need it. Completely unnecessary field. Yeah. Just 7 errors. Okay, we see the horizon. Now this is going to be problematic. I should have scrolled down because this is where hard functions are. Okay, if I fix this, do I have something else? Okay, start zoom, do it like that. Yeah.
Is SkiaBTW more for generic stuff like SDL, or more like U library?
It's very different from SDL. It's just a drawing library. The most stuff that you would do with it is the SK canvas. If you look at the API of this class, this is basically the whole Skia. The whole Skia is built around this canvas thingy. Everything else is just to support this. And canvas is this very traditional drawing kind of interface. You can access the pixels somehow. You can transform it using transforms, and you can draw a bunch of primitives. This drawing is... This is where the meat of Skia is. It's not that much functions, actually. Yeah, public interface is pretty reasonable, but it works wonderfully on basically all platforms. All platforms, all rendering engines. I mean, Metal, Vulkan.
reminds me processing.
Yeah. It should. Okay, just two missing pieces. So there is some C++ weirdness where it doesn't, I don't know why, where it doesn't want to convert from a simple, oh, this is because it's a const vector. To cast away the constness. Nothing that can be fixed by a strategically placed ampersand. I guess it also applies to Rust's borrow checker. Okay, this is current offset. Oh wow, it's a linear scan. That's crazy. Huh. So it was a good refactoring. You can tell that because all of the code became just naturally shorter. And I can fix the last error now. We have a special case, weird special case. I give it 10% chance that it will work. It will definitely compile. But the question is it going to run properly? Maybe less than 10%. Yep. Oh wow. At least the total time is correct. Oh, look at that. What happened here? I am concerned by the fact that it's not crashing. Somehow clicking fixed some issues. Can I play it though? Is it going to move the mouse pointer? It plays correctly. The 0. Do we need the 0 here? Zoom. Can I track zoom? Oh wow, I messed something up. It's going to be a pain to fix. Update child transform, I think. So whenever I do tick, I'm calling this function timer now. Okay, we'll do a quick break. And let's continue in a couple of minutes. All right. I think update child transform has some issues. Nice to look at the previous implementation of this function. The differences should be clear. This is the point where version control becomes useful. Library timeline. So we need distance 2 seconds. And max track length, but we are using floats divide. Okay, this was the issue. That part should work. There are still some problems. Oh wow. Oh wow, it's showing stuff. Okay, now there is an issue with the timeline dragging. The initial click is fine, but then the movement has the problem. Okay, this is the same kind of issue now. Again, something is not being divided properly. Maybe this max track length. I am using this in more places. Oh yeah, here. Suddenly it works. Snapping doesn't. Snapping has issues. It's reasonably responsive here. It's very responsive here. Snapping causes weird jumps. Insane jumps, actually. I zoom in. We are getting there, slowly. What was that? Why are we suddenly snapping? Are we snapping to the end of the track? Okay, so that works. Zoom also seems to work. The remaining issues should be in the snapping code. To check something. So the timeline now has just 168 bytes compared to, I think, 700 before the refactoring. The widget, 300 bytes. So nice. Enumerate the problems that we still have here. So, moving this. There was this, and there was also this weird snap at the end. I move the bridge, and here it suddenly... It doesn't do this now. Oh, no, it was a regular snapping. I forgot. This track, the track with F3, actually has a very tiny point here. It was snapping to this point. There is one more thing which I haven't even attempted to test, which is this splicing action. The display looks good. Yeah, so just 2 more issues, and this should be good. So drag bridge action, this is the one that we are interested in. the update function. So we added some extra checks. They are not active anyway. Taking the current time. Within the widget, yes. Okay, I know why this will be wrong. Actually, no, I'm not sure. Should work now. Now there is no black bar on the right. You can play it very fast. Okay, this crazy snapping. The last issue. Snap to track. Looks like this could be wrong. I don't know why, but so when I drag this and I move it to some point, eventually it gets it right. It just takes a while. I think I know what's the issue. The issue is that this current offset now accounts for the current bridge wiggle. Okay, looks good now. I do this. I need to do the same here. Oh, that should help. I should be able to grab this here. Now it snaps to full seconds. And I can also snap to full seconds like that. I want a value that doesn't include animation. Because I think it will be useful in some places. Current offset row. So when we create this widget, we can do no, it's enough if we just take zoom. It's just where animation starts. I say this is valuable because in Draw we can actually do highlighting for the bottom ticks, splice action, not screws. So this is the drawing code. So this is one place where we need to access the row value without animation, because we want to highlight the currently snapped point immediately. Doesn't work. Let me try again. So let's start from this. Current team. Wasn't that bad. I just changed it in a wrong place. This is what I wanted. I wanted to see this orange circle highlighting the current point. I mean, the current event, because we are chunking mouses into those very granular events. Okay, I think this was it. This was quite an adventure. This whole object was causing so many issues, but now it has been modernized. We switch here, back to our to-do list, and check this one as done. There are still some issues with key pressers. You can see that the point where the cable arrives could be positioned better. I think we'll also have to fix this. But I'm not sure if this is what we'll be doing on Friday, or maybe something else. Because we've been in the process of adding new mouse functionalities. So maybe recording for mouse up and down is more in order now. Anyway, we'll see on Friday. For today, that's it. See you next time. Bye bye.